Hola, ¿qué tal muchachos? Hoy aprenderemos acerca de los depósitos epitermales con el doctor Jeb Hedenquist.
Yeah, just outlines. Everything we will return to. Porphyry deposits, like you see in the east. The name is what's the name? Zenken. Zenken? Yeah, Zenken. Looks like porphyry deposits. Porphyry deposits are responsible for 70% of world copper and about 40% of world gold, except for placer, South Africa. And these form related to subduction. We will not discuss subduction, but it's important to know that the porphyry deposits related to oceanic subduction beneath either oceanic island arcs like Philippines, or beneath continents like Chile, Peru, Ecuador. Ecuador now with active volcanoes, and also Ecuador in the Jurassic. But also, epithermal deposits are in the same environment. So it's important to understand porphyry and relationship to epithermal. Now, this general schema also has said hosted copper deposits in rifts, extensional zones, but I don't know anything about that, so I will not discuss that. Just subduction for this lecture. Again, just concepts, introduction. Where are the major metallogenic belts? Basically, these are the belts, many of the belts of porphyry and epithermal deposits. We have Eastern Pacific, Miocene to a very younger, but also older. Jurassic in Patagonia, Jurassic in Ecuador. The same belt related to subduction of Pacific plate underneath the Americas. The same in Western Pacific. Very young volcanic arcs, but also Cretaceous in northeast Russia. Then we have the Tethyan belt. Tethyan belt was related to closure of Tethys. En español, Tethys? Yeah. Tethyan Ocean during the Eocene, Cretaceous to Eocene to Miocene. So older, from through Tibet, Iran, Afghanistan, Turkey, and Eastern Europe. And then Paleozoic. Fewer deposits in older times. It doesn't erode, but we also can have Paleozoic volcanic belts related to Paleozoic subduction. Here and in eastern North America. So again, this is related to subduction, oceanic, or continental, and we have porphyry and epithermal related to shallow intrusions in both cases. Fundamental shallow intrusions, because that provides the magmatic fluids, magmatic water, lava, gases, sulfur, chlorine, and metals, cobre-oro, plata. I'm a magmatist, not leaching. In Espanol, leaching. Yeah. Not for porphyry epithermal, not. Lixiviation? Yeah, I thought lixiviation for alteration also. Okay, lixiviation? No, not important. For the metals, those are coming from magmas. Very important. We have one other epithermal. Hello. One other epithermal environment, tectonic environment. Not arc, but back arc, extension. In this setting, no porphyries, only shallow epithermal. We will compare and contrast these two tectonic environments for epithermal this afternoon. Sorry about the colors, but we can use names: high, intermediate, low, sulfidation. But names are not important. No es importante. Okay? We can call them in Espanol grapefruit. Grapefruit? Grapefruit. Grapefruit in Espanol? Or
frutas en plata.
Yeah. Naranja? No, it's not naranja. Grande?
Naranja.
Yeah, but another. No, we have naranja and grapefruit are larger. Citrus.
Okay. I don't know the name.
Okay. Uva?
No.
No, uva.
Es más grande que la naranja. Toronja. Quizás.
Toronja. Yeah. So let's just call it toronja, naranja y manzana. Okay. Solamente nombre. If we want to look for naranja, we must go to the store to buy oranges. We must know what's the shape, color, what's the texture, what's the smell, what's the taste. These are characteristics. To explore, we simply need to know the characteristics of what we are looking for. Versus naranja, well, different skin, different, and this is citrus. In Espanol, citrus? Citrico? And manzana is different, but all together is fruta. All together, EPITERMALES. But these EPITERMALES is un poco diferente from this epithermal. So the name is not most important. The characteristics are important. Names not important. Okay? Because sometimes, no say. Okay, is this manzana overprint on naranja? Overprinting? Or is this hybrid, genetic hybrid, with characteristics of both? It's possible, maybe. So, first describe characteristics, and then look for features. Is it an overprint, or is it something? We have N member in Espanol, N member?
Extremos.
Extremos. Extremos, naranja, manzana, and then mixto. It's possible. But to start, we must know extremos, characteristics de extremos. Okay? Remember, nombre no es importante. I don't remember everybody's name here. No es importante. No. Only the good questions. Buenas preguntas is important, and people with a smile and very energetic. That's important. The names does not change who you are. Each is individual. Gracias. So, okay. Bien. Elena, you started introduction. It's we're focused on subduction, porphyry, epithermal environment. Related to subduction. Different volcanic arcs, porphyry and epithermal. Now we are looking at porphyry epithermal. The names are not important. Most important the characteristics are important. Just like if I forget your name, at least I know you're a beautiful woman versus an old man.
That's not true.
Characteristics are important.
That's not true. A veces también, sometimes looking for the characteristic, you can make a mistake.
Okay.
Not so much.
No, by definition, hombre, and what do we say? Old, antigua.
Viejo.
Yeah, those are characteristics. And female, and also beautiful characteristics. I didn't make any value judgment.
No, just sometimes you can make a mistake looking for a characteristic because you don't recognize the good characteristics. You make a mistake for the characteristic. For example, maybe it's a man. It's just look.
We will not discuss. We will not discuss
everyone.
No, great. Okay. So, names are not important. But, okay, because it's possible. We have extremos, naranja, manzana. But what if we have, this is the skin, manzana. Inside is naranja. So, okay. Is it one overprinting the other? Or is it genetic hybrid? Hybrido? Yeah. So, it's all important, okay? So, very general introduction. I'm not a specialist on subduction. But very simply, we have subducting ocean plate with alteration, sulfate, sulfur, chloride, and then as the temperature increases, there's dehydration. We get agua, sulfuro, chlorido coming up, and in the subarctic mantle there is magma melting, rock melting, rises through the crust, and then major structures focus the magmas, and then the magmas focus the hydrothermal system. Porphyry copper deposit, PCD. So, of course, muy complejo, but from a simple idea, this is how it works. So the magmas are important, and the evolution of magmas is important, but also the crustal permeability. In Chile, this is Falla de Domingo, but then cross structures, just like this. Those cross structures are important for focusing the deep magmas. And here are major porphyries: Chuquicamata, El Abra, Escondida, El Salvador, etc. So major structures, permeability, important for magmas, and then also important for hydrothermal systems. So think about that. You have your structures. In this region is called, the name you put for your region?
The name is Kutuku, or Kutuku.
Kutuku, okay. The Kutuku,
the name of the Cordillera.
yeah. The Kutuku arc, you already know major structures from your interpretation. Everyone has seen the map, major and minor structures. So you already know something about this. Okay, now we have subduction-related volcanic arc. The magmas, they are large batholiths, maybe 10 kilometers. But not just one batholith. Many intrusions, different age, and then the batholith, there's apophyse. In Espanol, apophyse, a finger, yeah, coming up. 1, 2, 3. 4. And these are related to the porphyry. Now, the age versus the amount of copper in porphyry deposits, it looks like some are very old. But then, if we look at the older deposits, these are different dating methods. Argon, uranium, lead, rhenium, osmium. Sometimes different dates, methods do not agree. So maybe we can exclude these and look. We can have very short life and a lot of copper. So it's not necessary to have millions of years. Maybe 100,000 years is important. So single hydrothermal systems forming porphyry deposits at shallow depth, 2 to 3 kilometers, maybe only 100,000 years. But in a district, you of course can have 1, 2, 5 million year life of the district. But these are different hypotheses related to the batholith. So we do not need long periods. Short life is okay for forming large deposits. Okay, we move from the batholith. Now let's look at this environment. So the batholith at 5 kilometers depth. These are apophyses coming up from the batholith. So the batholith brings awa, chloride, chlorido, sulfuro, and metals, cobre-oro. And then we develop, we have what we call exsolution. As the intrusion crystallizes, it exsolves the awa, magmatic fluid. So that arises, and eventually this fluid separates to brine and vapor. The brine is high salinity. The vapor, low salinity. So in Espanol, buoyant. Yeah. The vapor rises. The vapor rises, the brine stays at depth. The vapor rises and discharges from a volcano. Okay? So, the level of brine vapor is our porphyry environment. 1.5 to 3 kilometers depth, más o menos. But then at the shallow level, menos 1 kilometer, is our epithermal. And it's possible to have this relationship because porphyry is magmatic, cobre is magmatic, but in epithermal, oro is magmatic. No lixiviation, it's magmatic. Now we understand. So the batholith is important. The hypotheses are important for alteration, but also metals. Preguntas? ¿Español?
simple concepts, mucho detalles, yeah? But this is just the introduction. We will talk about this process, the alteration and metals in future slides. Okay, let's move from the schema to reality. I wonder if we can change any experts or
¿Quién conoce mejor el aparato?
can we make this darker?
Para ponerle
Más contrast?
Más sombra.
Paul, do you know projectors at all?
El experto está aquí.
You should menu.
Should be as great as
Menu. Más mejor.
That's the biggest hole in the world, isn't it?
Either this or Chuquicamata. I'm not sure. The important thing is that now maybe not, because there's landslides filling it in. Chuquicamata also has very threatening. The wall is moving at Chuquicamata. They monitor it. For that reason, both of these deposits are going underground. Chuquicamata has already started here in several years. Okay, let's go from this schema to real porphyry deposit for the details. What is the magnetic fluid that is providing metals? Okay. Here is pre-mining surface. 100 años antes. 120 años antes. Now, this is the pit. And notice there's current, elevation, and paleo. There's been tilting. So this is tilted back to Eocene times. Okay? So we have equigranular monzonite, quartz monzonite, porphyry. Younger, 0.7 cobre, 0.35 cobre, and very deep drilling. So Patrick Redman, now exploration manager with Tech, he did study here, and he sees that at depth there is this magmatic fluid we call critical, single phase, not vapor, but high temperature, single phase. But we see tetrahedra. Tetrahedra is calcoprita. So this is parent. Español? Parent? Parente. This is the pórfido de parente. This copper can be up to 0.5% in agua. Incredible. Huge concentration coming from the magma. And this fluid rises So we have critical fluid, critical fluid, critical fluid, but at this level, we start to get other fluid inclusions. Sorry, these are inclusion de fluidos in quartz. Okay? So this is quartzos. And these are the inclusions. So at this level, we start to also get vapor, known as cobre-oro, and hypersaline. Our liquid is liquidos. Yeah. So we have halita, silvita, hematita. So this is called the brine, or in español, hypersaline, mucho sodio y potásico chloridos. But these two are coupled. They form from the critical phase. The critical phase rises, lower pressure, and then separation. So above this level only, brine vapor, brine vapor. Now the brine, mucho chloridos. So it's very dense, heavy. Density is Eisen. Yeah. So this remains at depth. Deposits chloride or deposits copper, cobalt. Vapor is already old brain, also old and small brain. One of my characteristics. So buoyant is in español. Buoyant. What is buoyant? Yeah, you said before, buoyant? Low density? Buoyant. Yeah. It's vapor, so low salinity. Yeah. So this rises. This rises so it separates. Why is this important? Because different alteration. One style of alteration here, one style of alteration here. So,
sorry,
yes,
can we just go through this again?
Sure. Yeah.
Okay, so you've got this critical phase up to about 2.5 Ks.
Yeah.
And then it starts to separate. So
At this level, right at this level, we see appearance. Below is only this.
So copper is in solution here.
Yeah, that is the single phase magmatic fluid. Here, this is room temperature, but at 500 degrees, this is a single phase with copper in solution. Now it is present at room temperature.
None of this is precipitated.
No, this is all a single phase with copper in solution, 0.5% copper in the liquid, the parent liquid. And then, as the pressure decreases, we get to the solvents. I didn't want to go into those details.
So again, so this is phase separation.
Say at this below the copper deposition, we get phase separation, and above, simply then we get these styles. This is parent, and these are daughters. Maybe you could say daughter and son of the parent liquid.
Okay. And so, okay, and then you're talking, so the mineralization only goes down to here.
Yeah, apparently. So it's above the level of separation. We don't get copper precipitating down here because it stays in solution too high.
Yeah.
Simple, very simple idea is that it is the cooling that causes copper to deposit from this brine.
Yeah.
And the reason that it's important to know this distinction is because the vapor rises and that vapor causes alteration, like at Kinskocha.
Yeah.
Whereas the copper stays behind in the hypersaline liquid to precipitate.
Okay, just really.
Sure.
Yeah. Entonces, esta es una situación comprobada por Binghamton, que es en los Estados Unidos el pórfido más grande en el mundo, o bueno, Chuquicomata puede estar el mismo tamaño, pero estuvo en producción para 105 años. Entonces, este es el tipo de yacimiento que estamos buscando. Y una cosa absolutamente crítica es que, bueno, ahí todo el sistema estuvo virado tectónicamente, entonces pararon el sistema. Entonces, este es el palio a profundidad. Y algo crítico es que el pórfido sube obviamente desde profundidad. Y aquí no tiene cobre. No tiene, porque por la profundidad y la temperatura, el cobre está en el fluido. Entonces, es fuente de cobre, pero no tiene cobre. Porque el cobre estuvo en el fluido que estuvo subiendo. Y llegando a este punto, que era como 2.5 kilómetros de profundidad, el gas sale del líquido. Entonces tenemos un líquido aquí en profundidad y en este punto el gas se para. Y el rato cuando el gas está separando, empieza a precipitar la mineralización. Bueno, hay un gap de medio kilómetro aquí, no entendemos eso. Pero básicamente es la separación del gas que empieza a precipitar el cobre. Entonces el yacimiento, aunque todo el cobre pasó por esta zona, es un canal nomás, porque no hay manera para el cobre a precipitar. El rato cuando tú llegas a este punto, cuando empieza a hervir en un sentido, el gas se está separando, ahí empieza la precipitación del cobre. Y Jeff está diciendo que este líquido tiene un contenido de sal sumamente alto, tiene una salinidad muy fuerte.
En 50%.
Wow. Entonces tiene 50%
50%
de sal este líquido.
This is más o menos 10%,
Okay.
but then this increases to 50%. Why? Because we remove the vapor.
Yeah.
So we concentrate, by boiling, we concentrate the salinity in the liquid phase, and the vapor then is going to...
Entonces 10% de sal, 50% de sal, porque el vapor se escapó y concentró el sal en el líquido. Entonces, aquí estamos hablando sobre la precipitación del cobre, lo que está pasando con el cobre. Y ahora Jeff va a empezar a hablar sobre la alteración, y por esto tiene dos flechas aquí, porque lo que está pasando en reacción al gas es diferente a la reacción del líquido. Entonces, por estas dos flechas, uno gas, uno líquido, vamos a tener dos tipos de alteración. Pero la historia del cobre es muy simple. El cobre pasó por aquí, este es el origen del cobre, pero no hay nada de cobre, porque pasó. El rato cuando el fluido empieza a botar su gas, empieza la precipitación del cobre. Y ahora empezamos con la alteración.
Tengo una pregunta.
¿Y qué pasa en la alteración, en el fluido crítico? ¿Tenemos algún tipo de alteración?
Bueno, empezamos con la alteración ahora. Pero buena pregunta, Jeff. Información nueva sobre eso.
We do not have much information at this depth. Bingham, we have deep drilling. But usually, most porphyries, drilling, perforation stops. When the copper stops, perforation stops. So this is relatively unknown. But there is alteration here of potassical, biotite, K feldspar, but no copper. The copper deposits up here. So if we only looked at the alteration, we would not see this clear difference. When we look at the sulfides, we have no bornite chalcopyrite here, and here we have bornite chalcopyrite. So the main difference is in the sulfides, not in the alteration.
Ok, entonces potásico.
No.
En profundidad aquí, y el potásico no puede ver esta evolución del estado de gas, entonces la potásica sigue. La única diferencia es la potásica aquí no tiene sulfuros de cobre, por lo menos, y aquí tiene, pero la alteración potásica sigue.
Sorry. Solid alteration?
Pardon?
Solid.
Solid.
Albite.
Oh, yeah, it does start to become details. Albite, often deep albite related to meteorica being heated and depositing on the deep margins. If I had 2 full days, I would go into more details of the porphyry, but these are more general concepts. But we will have more discussion of porphyry. This is introduction concepts. Okay. Now, notice paleo depth, 1.5 kilometers. So erosion of 1.5 kilometers. Therefore, this is the pre-mine surface. This is the pit tunnel. This is the intrusions. And this is the stratovolcano that was present at 38 million years. 38 millones años antes. And based on mapping, etc., this estimate. Mafic dikes may be important, syn hydrothermal. So we had the brine, but then this is the vapor. So the vapor is discharging from the stratovolcano, and the arguing is that there was a lithocap of advanced argillic alteration. Was there a Kimzicocha forming over Bingham? No say, it's all eroded. But it's possible. So that's the important suggestion that we will keep discussing. The link between porphyry and epithermal alteration, the link between porphyry metals and epithermal metals. What's the porphyry west of the 5 million year porphyry? Near Rio Blanco. Chaucha. Oro at epithermal depths. Okay? Claro? No problem? We will look at examples, more real examples. So, Bingham's stratovolcano. This is possible with advanced argillic alteration. So where are the examples to study? White Island volcano in New Zealand. Did anybody read this morning? Yesterday, eruption. 20 personas is missing, presumed dead. I didn't know this when I put the diagram in. So this is quiet eruption. No, it's peligroso, but every so often there's bang. And yesterday, only yesterday, there were at least 50 personas, turistas, looking around by boat, by helicopter, during the eruption. So, high temperature discharge, mostly high temperature vapor, agua, con hydrochlorica and SO2, sulfuro dioxide de sulfuro. Okay? And on the ground, high temperature fumaroles, lower temperature fumaroles. That was in 1988, 30 años antes, más o menos. 2004, no hay eruptivo. But Crater Lake, agua meteorica, but also must be magmatic vapor. Why? pH 0.2. If you take your picota with a rubber handle and put it in this, una hora, no tiene picota, solamente rubber handle. Why so acid? Because of the magmatic acids. And when this overflows, it comes along this stream, discharges here. This is dissolved andesite. This is ferro, aluminum, from the lixiviation de andesita, and that's flowing off to the ocean. Still very acid. It's dissolved andesite, lixiviation de andesite. And the residue is quartz. The iron, aluminum, sodium, potassium, calcium dissolved in the rock, and only silica residue left. We call this residual quartz or vuggy quartz. In Ecuador, the Kimzacocha, what do you call this? Silica residual? Or vuggy. Yeah, vuggy. And we cannot see close up, but this is vuggy quartz. Originally, this is rhyolite here in Japón, but this is now 97% silica because of lixiviation. Here, the vapor condenses, very acid waters flow through. We'll come back to that in 2 more slides. So let's look at this crater lake. Oh, no, sorry. We'll come back to that later. This is Satsumi Ujima. This is Domo de Riolita with, again, high temperature vapor with also acid volatiles. and thermal springs, baños, muy ácido, 1.1, 1.7. We collect samples of the vapors, so we can analyze chemical compositions. We have to wear rubber suits because this vapor, if it condenses, we get acid. We get the HCl going into solution in the sweat around eyes, etc. So the same acid that is attacking the rock, we can see the lixiviation. And we can see the, just like White Island, lixiviation, the dissolved rhyolite flowing off to the, here we have iron rich, here aluminum rich, the white flocking. So this is the environment. We were looking down. This is the outflow of hot springs, but acid, the outflow to the ocean. To show this is lixiviation, this is ppm. So 1 million ppm, that's 100%. This is 1 ppm. So for rock forming elements, sodium, potassium, calcium, magnesium, aluminum, iron, rhyolite fresco. This is fresh rhyolite. This is the composition of acid springs. So we see isochemical dissolution, lixiviation, the isochemical. Simply dissolving everything except silica. The silica is residual, and so we get lixiviation. So, this point, is it clear? We need to discuss this in español.
¿Estamos bien?
Yeah, okay. So, very simple evidence that the magmatic vapor is condensing, leaching the rock. We're getting cristobalite with up to 97% silica. This is realita, but now 97%. Alinita, so advanced argillic alteration, menos 30 ppb oro. So this is sterile. Alteration, advanced argillic, but sterile. So at Kimzicocha, there must have been another liquid con oro, plata. So the initial alteration, and this is what this is the environment producing, for example, Summitville gold deposit, like Kimzicocha, residual, vuggy quartz, or quartz elinita. Let's see. Yeah. This is the etapa de lixiviation, the first stage, and it's sterile. So to form a deposit like Kimzicocha, Loma Larga, we need later liquid. We'll discuss that later in the lectures. But this is the concept, introduction. Okay? Now, I understand that in this region, knows lithocap? Julie? Tiene Kimzicocha in Jurassic? No? So maybe It's all been eroded from the east. We're now down to the level of pórfido. So, but still important to understand the relationship. And maybe you will find some lithocap, some of this buggy quartz, more fieldwork. Okay? So, ¿hay preguntas? No? Okay.
The fluids are coming as fluids?
Well, no, this is the vapor, and the acidity is when the HCl SO2 forms acids, condensation. En español, condensation. Yeah. I will return to the alteration a little bit later. This is introduction. Okay? So
just
yep.
one question. So we should have this kind of iteration also around the conduit below where the vapor is coming. Yes, the conduit himself will be affected by the vapor.
Yeah, but maybe only several hundred meters depth, like at Kimzikocha. When we review Kimzikocha later, you'll see the alteration distribution, the shallow levels, and then the conduits.
Yeah.
So let's wait for the details later, but yes, it's possible, but usually not down to the pórfido level. No, it's over the tops of the pórfido. Okay?
The first statement of the lixiviation,
See?
there is well,
Menos, aquí, menos 30 ppb. So no es oro de depósitos. This is only anomaly. In your porphyry to the east, what's it? Sunken? Yeah. ¿Cuántos oro? Menos detection.
Yeah.
Menos 2 ppb.
Yeah.
Okay, well,
Well, for the moment.
pardon?
For the moment, we never had mineralic date sample there.
Yeah. So far only soils mainly.
Yeah, so I mean, soil there is no.
Yeah. But, yeah, just wait for others. But alteration affected by vapor, no tiene oro. These are analyses, so very low. Okay. This is the first stage. We'll talk about mineralization later, metals. So, let's look at the stages of formation of porphyries, particularly alteration, zonation. Now this is a now famoso, muy famoso schema by Silito, 2010. I can give you the PDF. And this is the porphyry sistema de pórfido. We have deposited yacimiento de pórfido de cobre, intrusion, but the alteration and everything is the system, not just the porphyry deposit. Okay? So the first stage, high temperature stage, coupled brine vapor. Remember, we have the critical fluid separating the brine and vapor. These are linked. Linked, coupled, en español, coupled.
Relacionados.
Son juntos. Claro.
Yeah, one exists because of the other.
Los dos van juntos.
Yeah, they're linked.
What is brine again? I don't understand.
I'm sorry, what is?
Brine.
Brine is liquidos de hipersaline. Brine. 50% sodium chloride. Yeah, very high salinity. We can also say hypersaline, but that's a longer word, so I shorten it using slang. Brine is very high salinity. Brine con cobre, vapor sin cobre, sin oro. Vapor con itself. This is forming the brine. Okay, we back up. So we have magma, intrusivo, then critical phase, liquid, exsolution, rising, and then lower pressure, we get separation. The brine, liquidus de hypersaline, and the vapor. The brine is dense, stays at depth. The vapor is buoyant, can ascend. Okay? And the vapor, like at White Island, may discharge to the atmosphere. But some of the vapor, due to mixing with meteoric waters, some of the vapor condenses. And the vapor, we get condensate with sulfuric acid and hydrochloric acid. These acids come from the vapor. Okay? Like we saw at White Island, in Satsuma Iwajima, the very acid condensates. And proximal, we get lixiviation. Silica de Voghi, okay? And alteration halo, quartz elinita, quartz kaolinita. These form the lithocap. Lithocap is a new term for the lithology, lithology that caps or overlies the intrusion, so lithocap of advanced argillic alteration. Quartz de lixiviation, quartz elinita, quartz kaolinita. In Kimzakocha, this type of alteration over 6 kilometers, 8 kilometers?
No.
Yeah, no?
Yeah.
Más o menos? En Kimzakocha. 10? Okay. But the metals, much smaller area, only proximal. Most, at Kimzakocha, most of this alteration is sterile. Okay, so, but remember, this is the early etapa una. Okay? And I should say, this is now still sterile. This alteration at this stage is sterile. But then, the magma is cooling. We have the magma here. We have the critical fluid rising, but it's now cooler with time. And because it's cooler, it never separates. to brine vapor. And so this primary, this critical liquid continues to rise. And the alteration, now this is the magmatic composition, about 10%, and this continues to rise through the system, resulting, we get chlorite, cerussite, or white mica, alteration, overprint. The initial alteration, biotite, butita, K. feldspar, this is now overprinted by chlorite cerussite alteration related to this lower temperature magmatic fluid. And because this is now low salinity, this liquid may rise into the lithocap. And this liquid contains metals. Remember, this is the magmatic liquid. It's rising, can add metals to the porphyry, but it also can bring metals into the lithocap. Energita, oro. So this is etapa 2, con oro, plata, cobre. So like a Quimsacocha, Loma Larga, we have energita, 0.4% cobre is energita, con oro. And where does it deposit? Mostly in the proximal silica residual. This distal alteration, still no oro plata, oro, cobre. Okay? So this is the simple concept. Each porphyry and or lithocap can be much more complicated. But fundamentally, this is the concept of how this system evolves, how we get shallow alteration and overprinting, and introducing metals to epithermal. Now, what happens if no tiene? If this fluid does not reach the lithocap, we can have porphyry copper, yacimiento de pórfido cobre, but barren lithocap. But still, this liquid may be present, but rise along fractures. And if that's the case, then we can have vetas de oro plata, such as there are pequeña vetas de pequeña vetas Quimsacocha al sur. Pardon?
The name?
Yeah, the name.
Tusky is the name.
Tusky, yeah. So it's possible to have a barren lithocap, and we will look at examples with intermediate sulfidation veins nearby. So we may also have vetas de oro plata related to porphyry. Okay. And this is the stage of formation of veins. Okay? Richard has escaped, but if there's any questions, maybe others can answer, or JP.
When we mineralization in the porphyry or in the system?
For example, in Filipinas, Lepanto, 4 million ounce gold, 1 million tons copper. The porphyry, 5 million tons copper, 20 million ounces oro. You know, you can have both, mineralized, or you can have a barren lithocap but still metals in the porphyry. So there's not a relationship between metals in epithermal and porphyry. Barren lithocap, still mineralized porphyry. That's possible. Now, we do not have lithocaps here, but they probably existed, but they've been eroded. But someday, maybe the experienced, others perhaps worked also, but certainly Gilly and Franklin, experienced with Kimsgocha, maybe you'll find. Half of your region, not even stream sediment sampled yet. Yeah? They may be out there. They will be cliffs, very difficult to get to.
We already found some ruby quartz.
Some
Ruby quartz gold.
Oh, but float.
Yeah, float.
So I can assure you, the lithocaps were there, maybe now eroded. The fact you have porphyry targets suggests erosion is below the lithocap level. To the east, but to the west, maybe there's still some hiding in the jungle. Okay?
In the first step, there was a little gold, a few gold, less than 30 ppb.
Yeah, at this stage, this is sterile. Muy.
Yeah, in the second step, more gold and copper.
Yeah, because, okay, en vapor no tiene cobre, no tiene oro. Sulfuric acid, HCl, yes, but no metals in the vapor. In the second stage, this is liquid. In the liquid, it's possible. Oro, plata, cobre. It's that simple. The metals travel with the liquid with the high salinity, not in the vapor. Okay? So that's the concept to get. It's possible to have barren alteration if it was related to the vapor. Okay. One last set of slides, 2 slides, and then we can have a tea break. How many people have seen this typical porphyry copper alteration pattern? Anyone? Okay. Yeah. I was taught this 1970. We have potassic, philic alteration, argillic, and propylitic over the top. Dash, 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 dash. Question mark. Why? Lowell and Gilbert worked in America Norte, laramide, 60 million year old. And I'll show you. Yeah, even now, some people like this model. But this model is not correct. So this was a start, but now it's modified. So why did we have this model with dot, dot, or question mark over the top? Why? Because in Arizona, all of these areas are eroded to different levels. At Bingham, this is erosion level. So the lithocap was eroded. Very old. Just like here, Jurassic. And that is why no lithocap. So the models, no lithocap. The model came from the Laramides, 60 million years old. And the lack of alteration. So we now know, no propylitic. This is lithocap, advanced argillic lithocap. From studies in Chile, in Philippines, Indonesia. Young porphyry and with lithocap still present. But very simple. So this model now has been replaced. Okay? Please remember that. I saw yesterday in a report that you showed that you were looking at some figures. Very briefly, I saw this model. And so you know if that person is using that model, they are missing part of the system, the shallower system. And yes, even here in the Jurassic, probably eroded to this level, but still we must understand what has been eroded. And there are Jurassic lithocaps. It's possible. Depends on the setting of erosions. There may be some preserved. There are even Paleoproterozoic mineralized lithocaps in Sweden, Finland.
Well, if we have paleosurface in the west part of the property, it's probable that if there is porphyry in the west part, we will have lithocap.
Yeah. Or vice versa. The lithocap, there's deeper porphyry. There definitely.
Yeah.
But maybe too deep. Like Kimzicocha. We see in the diatreme clastos de pórfido on cobre. But at present it's too deep to explore for. The focus is on epitemale, oro de epitemale. But the porphyry is there. Okay? So, how about if we have a break, 20 minutos, we come back and look at general zonation of alteration in porphyries. Okay?
Muchas gracias.
So, in 2010, we now have this general schematic model of porphyry systems, including the shallow environment, backing up, whereas the 1970 model only had the porphyry level. Now we know the shallow eroded part. And so we can now go forward. That model was muy simplificado, very basic, general. If we look at some examples, we see different styles of alteration, but there's one common factor. Although it's variable, all of them have zoning. For example, here at Hugo-Dumet deposit, a very high grade in Mongolia, we see sericitic alteration related to cobre, 2.5% cobre, very high grade, with chlorite sericite overprint of potassic, right here. But there's no potassic here, but there would have been previously. It's been overprinted, as we see here. And here, very strong overprinting, no evidence. but still we see some zoning. Here at Chuquicamata, well, let's go to El Tiene first. The intrusivo, mineralized porphyry with K feldspar, potassic. And then in the host rock, K feldspar, potassic biotita. And then further out is potassic propylitic transition with, and I'm always uncertain which is which. Maybe this is potassic propylitic and this might be chlorite sericite over potassic. I'm unsure of the colors. But the important thing is now a lot of potassic present with margins of white mica overprint. Yeah, different, but still some similarities. Here at Chuquicamata, we have to the east, we have potassic, biotite, K feldspar, the pink, sericite over potassic, and to the west, only sericitic, associated with high grades of copper. And this is asymmetric, here symmetric, but this is asymmetric, but probably there are two different times of system. One is, this is younger, probably overprinting this older part of the system. So the important thing to note is that variable zonation or variable alteration, but they're all zoned. See?
So where is the albite zone?
Okay, let's see. Do we have? Oh, Elbita. Please help me look for it. Yeah, there it looks like shallow albite at Ridgeway. Ridgeway is a alkalic magmatism. So a special type of porphyry, alkalic. But many times, albite should be on the deep margins. But remember,
This hard temperature?
yeah, well, albite forms on the deep margins as meteric water is coming in and being heated. But remember, on the deep margins, many times there's no drilling. It might be here, but no information. I didn't go into those details, but if you're interested, I can show you some diagrams later. So, variable, but some common themes, always zonation. So make your observations of mineralogy using hand lens and support by Terraspec. K feldspar, biotite, chlorite, muscovite. These can all be recognized with hand lens. Franklin's not needed. But still, it's good to have also, sometimes there's advanced argillic. As I'm going to discuss in the next lecture, advanced argillic is not a good term. Let's see. Because here, advanced argillic is actually porphyry. And that's where Franklin can come in very useful to distinguish white mica from porphyry. More difficult. Not for Franklin, but for others of us. Franklin can listen. Porphyry. So, is this lithocap? No. This is deep porphyry. And so I'm going to say we need to not use this name, and we should use mineral names. That'll be the next lecture. Okay? Apprentice? Again, this presentation is not details of porphyry. Rather, it's concepts and transition to epithermal. If you have a porphyry outcropping at the surface someplace, it's relatively easy. You just need to get into the jungle, collect your samples, and you don't need my help. Okay, veining. Very simple, much variation, but basics are simple. We have early high temperature veins during the potassium feldspar biotite stage, potassic stage. These are the A veinlets. And these veinlets are wavy. Wavy. Why? Because at high temperatures, the rock is ductile. It can deform. So initially, the A veins form, they're straight, but the hot rock deforms. And so the veins become wavy. The alteration is Cape feldspar, but the fresh rock has feldspar, so it's difficult to see the alteration. These form at lithostatic pressure. The B veins are transitional. The D veins, the intermediate stage, the white mica chlorite stage, lower temperatures, so now the rock is brittle. It fractures and stays open. So we get straight D veins. And now the alteration is white mica. So here is a D vein that cuts through with the alteration halo. And at this stage, the pressure is hydrostatic. It's evolving, the vein types are following the evolving potassic to white mica stage. Franklin?
The multi-type veins, in which state is it for me?
Well, next slide, or two slides maybe. Usually in the earlier biotite stage, magnetite stable, but sometimes later as well. But we'll come to that another one. So this is from El Salvador, Gustafson and Hunt, definition of ABD. Now, Silito summarized this: wall rock. All veins can cut wall rock, and all veins will cut the early porphyry. A veins, B and D veins. But if we have early intermineral intrusion, after some veins form, that intermediate intrusion, synhydrothermal, can cut off the earliest vein. And there are some vein fragments here. That's good evidence for intermineral porphyry. But still, then we have A veinlets of the intermineral porphyry, and B and D. And then the late intermineral, we have no A veinlets. It's lower temperature. We still have B and D veinlets, later veinlets. We may have a chilled contact, phenocrystales, because this may be cooling. And then finally, late mineral, post-hydrothermal intrusion cuts everything. And fresca, or alteration propylitica. So by examining the vein types present, sometimes a vein being cut That helps to identify early and later intrusions. And we see multiple stages of veins here. Early, then being cut by later veinlets. Very typical. And we cannot just say quartz vein stockwork. We have to look at the different stages, cross-cutting, because that will help identify which intrusion stage we're at. It's typical to have 2, 3, 4, multiple intrusions. For example, here in northwest Turkey, there's a quartz alunite lithocap that was being explored for gold potential. And let's see, no. The field assistants were collecting samples of the lithocap and stopping at the base of the lithocap. But one weekend, when the geologists were in the city having big dinner and drinking too much, on Sunday the geologists didn't come back, they were sleeping. The field assistants continued to run the line into the valley. The final 2 or 3 samples were the best anomalies. On Monday, oh, you should have stopped the line here, you wasted it. 3 weeks later, results come back. Great. And they went into this area of outcrop in the valley with stockwork quartz veins, with cobre. So the lithocap was barren, but in the valley adjacent was outcropping stockworks. Small, 250 million tons, 0.3% copper, 0.3 grams gold. But still a nice little discovery. And as we can see, the quartz alunite lithocap is on the shoulder of the porphyry, not over. We'll discuss this more later, but it's on the shoulder because there's ascent and lateral flow. So that's one important concept. The strongest lithocap is not over the porphyry, like at Kimsikocha. We'll see that diatreme with porphyry fragments are here, but the lithocap is along structures away from the porphyry. We'll come back to that. Okay. The discovery hole, about right here, 300 meters, 0.5%. Copper, 0.5 grams gold. The early porphyry, 1 gram gold, 1% copper or more. Intermediate intrusion, 0.6, 0.6. Why? Because this is a younger intrusion. Not as many veins. And then the late intrusions, 0.2. And this is dominant, the late intrusions. So even though we have high grades in early intrusion, 1 gram gold, 1% copper, it was diluted. In Espanol, dilution. Yeah, dilution by intrusion. So unfortunately, if all the deposit was early intrusion, it maybe would have been 1 gram gold, 1% copper, but many late intrusions. So average grade, 0.3. This is a good example. Many veins, few veins. And that's typical in porphyries, so something to look for. Okay? So if you're mapping vein density and you find very low vein density, maybe it's because you're mapping at the surface a late intrusion. Even if there is some alteration in metal anomaly. Okay, so multiple intrusions are important. Defining. Of course, if it's jungle with no outcrop, it's very difficult. It's something to keep in mind. Okay, coming back to Franklin's question. This is Los Pelambres in Chile. We can see vein density. Highest vein density in through here, near the open pit. So that's the highest grades, related to the highest vein density. Now here, let's see, here there's an early biotite rich vein cut by A quartz, here. Here we have magnetite bearing A vein. Let's see, let me carry, cut by, here magnetite only veins. Sometimes we have only biotite or only magnetite, early veins. So magnetite only veins cut by quartz magnetite. Here's B vein with molybdenite, moly, transitional, and D vein. Here D vein with white mica, halo, pyrita, tenantita. We were talking about suddenly some areas having arsenic anomalies. Well, instead of copper sulfides, maybe we have copper arsenic sulfides associated with some later veins. So, different porphyries, different styles of veins. You simply need to recognize for one project what is vein style. Okay. Now, again, I'm not a specialist of porphyry veins, but these are simply observations. Back to Bingham. 3 styles of veins. Stockwork, K feldspar. Basically, this is A veins and K feldspar halo. We can see earliest 1, 2, 3, 4, and the student Gillian Gruen established cross-cutting, based on cross-cutting the youngest, the oldest 1 and the youngest. 6 cuts everything. Very complicated. But these are all early veins. And then quartz molybdenite, that's B vein, transitional. Quartz pyrite, white mica, D vein. So you can use A, B, D, or just describe magnetite veinlet, biotite veinlet, quartz veinlet with wavy, early quartz vein, late quartz veinlet con pyrita, más o menos tenantita. You don't need a name, describe. So let's look at shallow alteration at the surface over El Salvador, Chile. This is a deposit I did work on, not on the deep porphyry, but on the surface alteration, which is what we were interested in, to understand the deeper porphyry from surface alteration. In Chile, this is all muscovita. You can see the bleaching. And at the top, porphyta. So intrusions from oldest to youngest. 44, 43, 42 million years. 44 a 42 million years. Getting older, younger. And you can see other deposits right along the Domeco fault. Here is El Salvador. Okay, we will now look at this central area. We have andesite and rhyolite domes, host rocks. And then the earliest ex-porphyry at 44, granodiorite, K-porphyry, and then the youngest, L-porphyry, late porphyry, Vitardia. Here, this is 3,000 meters surface. This line is copper, cobre en 2000 meters. So 500 meters deep is copper. Sort of as a halo around the latest, least altered porphyry. Okay? So this is copper projected to the surface. And we see andesite here, X, K, L porphyry. L being least altered, but still some mineralization in L porphyry. But very regular zonation of calcobrita bornita, calcobrita brita, and pirita. This is at the ore level, about más o menos 700 meters deep. So very regular sulfide zoning. Alteration zoning, sulfide zoning. And here is a fragment or a rock from underground. What do we see here? I should ask some questions. Yes, quartz veins, but what about this texture here, texture there? The same intrusivo? No. Yeah, this is Phenocrystales grande, pequeña. So it looks to be some difference. What about veins? Yeah, so different styles. Veins. We have biotite here. No Tiene, nothing large. Pardon? Yeah, fewer veinlets here. And what about this right there? Clastos, xenolith de veta. So for this to be a vein clast, this must be younger porphyry than here. So one of these veins broken during this intrusion. So maybe somewhere in through here is the contact. It's difficult to see, but vein clasts give us evidence that it's a younger porphyry. So uno, dos, tres, and obviously tres, cutting the whole thing, cuatro, cutting tres. So this is younger, but 1, 2, maybe only within, certainly 1, only within the older porphyry. So we have to look for these features. So this is surface alteration. This is underground deposit, so block cave. Let's see, in Espanol, block cave was, pardon? Yeah. Okay. No, it's just collapse. So this is the collapse zone.
Collapse.
No, it's Tahoe, it's It's the zona de colapse because mineralization is 700 meters deep. So we're at the surface, least altered, late porphyry, and we see propylitic halo, but then large area of white mica, muscovite, 4 square kilometers. This is 1 kilometer, 1 kilometer. And proximal, muscovita, andalusita, and mucho andalusita in proximal area. This is from shortwave infrared, first hand lens, then also confirmation by shortwave infrared. And then pyrophyllite, perophylite overprinting white mica. And that's where the copper ore is. So if we look at that, we can now say empirically, if we'd mapped this alteration here, mucho andalusite and perophylite, we would have been able to identify proximal. To then say, okay, let's drill here, 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 and we would have probably hit this ore. Why? Why muscovite perophylite? First phase diagram, but very simple. Potassium hydrogen in solution. So mucho hydrogen, the ratio decreases and we have lower pH, more reactive. In temperature. High temperature, Cape feldspar. Cooling, transitional stage, we know we have muscovite and andalusite. So the fluid must have been cooling along this zone. Now, how do we get perophylite? First possibility is in lithocap, vapor condensation, con alunita, perita, in the lithocap environment, like Quimsacocha. But otra possibility is fluid cooling, simple cooling of muscovite will also get into perophylite stability. Here we have muscovite and andalusite. So we know the white mica stage overprint is this composition. So it has to cool into perophylite. And we see that muscovite, light gray, perophylite, dark gray. Replacement, retrograde reaction along the cleavage. So this is not perophylite in the lithocap. This is perophylite at the shallow white mica level due to cooling, simple cooling. And here we see perophylite overprint of muscovite zone. So not lithocap, but simply transition, late stage cooling. An important difference. We'll come back to this diagram when we're talking about lithocap perophylite, Quimsacocha. But for now, this is the importance. So I asked if there was any perophylite yet, but apparently not a lot of shortwave infrared analyses. No. Yeah. You've simply identified some white mica.
In second?
Yeah, second.
No, we didn't.
Oh, no, only in moistures from Hanlon's.
Oh,
Okay. I thought the sample you showed me yesterday was from Tengen with mucho perita y muscovita.
no, it was from Awakshap.
Okay, sorry, I was
Well,
confused.
the identification we made is cerussite.
Cerussite is a field term.
Yeah.
Cerussite is not a mineral. White mica is the mineral. Maybe muscovite, maybe illita. Franklin will be able to discuss these. So, cerussite is with Henlens. But as soon as we have shortwave infrared, what is the mineral? Is it illite, muscovite, etc.? So, fairly early in the Tsenkan assessment, try to get mineralogy, alteration, as well as differences of intrusions. Yeah, Franklin.
Please, again, how is the process to get pyrophorite from muscovite at a pore?
Cooling. No, not vapor. This is liquid. This is, remember, this is the philic stage, the transition. First, high temperature, potassic, feldspar, and then later, lower temperature, 350 degree white mica, overprint of our transitional stage. But in the final stage of the cerussite or philic overprint, we can actually have some porphyte. So this porphyte is part of the philic stage. If you like the term philica, I think we should not use potassic philic, but only mineralogy. Potassium feldspar, biotita, muscovita, periphelita.
For example, I saw in examples of the few muscovite.
Yeah. ¿Dónde? Senden, yeah.
Meaning something with the pórfido.
Well, maybe. I mean, it's consistent, but build up the alteration picture there. That will give you, it'll start to give you other information. You already have some zonation in the soil geochemistry. How does that correlate with the alteration mineralogy? Certainly, that's the next step. Even before geophysics.
So I think it's important that the geologists in the field, each time they identify different style of alteration, they take sample for then frankly check what is the mineralogy of the sample.
Yeah, first the mineralogy by Henlens. I think this. Please check. And then bring it back to the geologist and add first the field map information, and then another layer of shortwave infrared, and build it, and always come back to the geologist. So you can tell the geologist, oh, this is muscovite. No, illite. No, periphelita. And then you can start to see. Yeah, please, in español.
Entonces, esta parte, la zonación de la alteración de los pórfidos es algo muy importante. Como decía Jeff, ya vemos en la geoquímica una zonación, por ejemplo, en Quién Norte 2. Ahora lo que tenemos que buscar es entender las diferentes fases de intrusión, porque sabemos que tenemos varias intrusiones. Hemos encontrado en el campo, y es un buen trabajo, se ha cogido diferentes tipos de intrusión. Entonces, cuando estáis en el campo, la otra cosa importante es los diferentes tipos de alteración. Entonces, ¿cómo tenemos que trabajar? Cuando estamos trabajando sobre una zona de pórfido, es importante reconocer, usar lo que decía ayer, la lupa, siempre. Nosotros tenemos que estar siempre con la lupa, no solo mirar así las rocas, sino que ir a ver lo que hay dentro de la roca, siempre. Entonces, cada vez que estáis en una zona que veis cosas diferentes, es identificar y tomar una muestra de cada tipo de intrusivos que tenéis. Por supuesto, si hay vetas, diferentes vetas dentro, tomar también este muestra con la posición, claro, y también verificar con la lupa qué se ve dentro de la roca, qué son los minerales. Cada vez que ves, que identificas que hay, por ejemplo, una filita blanca, una filita negra, cualquier tipo de alteración que os parece, se coge la muestra con la posición y luego se la enseña al geólogo senior, que luego va a seleccionar las rocas que mandamos a Franklin para saber exactamente qué tipo de filita blanca tenemos, qué tipo de alteración tenemos, y después de eso, poniendo toda la información, y por eso la base de datos es importante, poniendo toda la información en el QGIS con Aleja, vamos a dibujar mapas de diferentes explosivos y mapas de zonas de alteración. Vamos a poner las zonas de alteración arriba de la zonación que vemos en la geoquímica. Eso nos va a ayudar a poner después los pozos.
Yeah, because that will then build up the information to allow targeting of drill holes for the best chance of the first drill hole being in the right place.
Pero también creo que puede haber una confusión, así mismo en el campo, como hay diferentes reacciones. Entonces, en la zona así intermedia, tiene que haber algún mineral o algo característico para poderlo diferenciar. Entonces, ¿cuál sería el punto ahí de ver cuál es? Porque ya sabemos que en la parte alta podemos encontrar una polita, cosas así, en la parte baja, pero hay una zona intermedia donde se van a mezclar todas las...
Es importante que se toma lo máximo de muestra, que no solo las muestras que son mineralizadas en este tipo de depósito, se toma la máximo de muestras diferentes que se encuentran con la posición. Siempre cuando estáis en el campo y que veis algo diferente, algo que no entendéis, porque no podemos saber todo, se tiene que llegar, porque tenemos la posición, la muestra, y una cosa es seguir haciendo lo que hizo José y Quién lo hizo también Jefferson, y que cuando se coge estas muestras, poner las muestras en el suelo, más o menos en la posición, y luego un geólogo senior puede venir y ver, ok, aquí, estas muestras son importantes, estas no, estas son alteraciones superficiales. Entonces, con la experiencia de gente como Robert, o como Osvaldo, Julie y Franklin, vamos a guardar lo que es importante, y luego Franklin nos puede hacer un estudio más preciso y podemos tener después no vamos a tener toda la información así. Es coger mucha información en el campo, poner en la basura la información que, bueno, no es nada importante, pero guardar la información importante. Tomar muestras que os parece raras. Cuando no entendéis, o si entendéis, por supuesto, la tomáis. Pero si no entendéis, incluso, bueno, por acaso la tomo y se la enseña al geólogo.
Tenía una consulta, si me puede ayudar ahí. Siempre vamos a tener varios cursos de intrusivos, en este caso allá en Senken tenemos esto. Entonces, la idea es de que el intrusivo más antiguo es el que va a tener alteración, ¿no es cierto? Y los más nuevos prácticamente vamos a tener roca sana o no necesariamente.
The question is what we are interested for is that oldest intrusive, because they will have more alteration on more.
Exactly.
Yeah. Or So we will be less interested by the younger intrusions.
Not less interested, it's important because if you find, like in Turkey, a lot of late intrusions, maybe that will have lowered the potential of the porphyry. So everything is important, even the non-copper bearer, because maybe that's extensive, and it says this project is low potential, but the project here, maybe few late intrusions, a lot of early intrusions. Well, maybe this is higher priority, because we only have so many people, money, we have to have priorities. And you are fortunate because you have multiple projects. So you have to rank your projects in priorities, epithermal and also the porphyry. So all of these observations, particularly at the early stage, are very important. But it is important, yes, also.
Yes, the question was that it's always the older porphyry intrusion that have the best mineralization, or it could
Yes.
be the older intrusion with very few mineralization, and then will be the medium age that will have more.
No, typically the oldest is the best. That's a generalization, but it's
Most of the time
yeah.
son los más viejos intrusivos dentro del sistema de variación intrusiva que van a tener más potencial, y las últimas intrusiones van a tener menos mineralización.
Yeah.
And so the oldest intrusion will have much more alteration than the younger.
Typically, but also it depends, like at El Salvador, the oldest intrusion is not where the main mineralization is. That also migrated, but then it stopped here, and multiple intrusions came in, and the oldest of the main porphyry is the best mineralized. And the least altered is, you can see, it doesn't contain much copper at all. But definitely establish the different stages to be able to assess which is the most important, which has the most veins. Usually the number of veins equal the amount of copper. Fewer veins, fewer copper. So, if we look at El Salvador again, we have Muscovita, late Profilita overprint, and then also very late Lithocap de Elinita right here. Why Elinita at the same level as white mica? This is not consistent. The lithocap should be shallower. So this very late stage is only related to late breccia bodies. We call it breccia dikes. So we have Elinita, Diquita, Diaspore, Kelnite, Periphlita. Some muscovite, but the muscovite is from the wall rock. And the lithocap is over here, quartz Elinita. So let's look at this stage. At the start, 42, there's potassic alteration in sulfides, but only in vetas, because potassic has been replaced by white mica and sulfurous oxidized. So we don't really see the potassic. But remember, if potassic, what does that mean? Potassic, hypersaline liquid. What is the coupled? The coupled part is the vapor, right? So the vapor should have risen. We think the paleosurface about here. So there should have been quartz alunite at 42 million years up here, like maybe at Sengen. It was up there, but it's now eroded. Then we had Muscovite overprint, and finally in the late stage, Puraflita. This is más o menos 42 millones años. And then quartz alunite lithocap and breccias. But this alunite is 38 millones años. 4 million years difference. So erosion and then younger lithocap. So that is important. This lithocap is not consistent with the Muscovite level, but now we know this is younger. So it explains, and it's common. So this alunite must mean there is a deeper porphyry intrusion. We have the 42 million year intrusion, zoned alteration, copper mineralization of depth, then erosion, followed by another deeper intrusion, and this lithocap. So be aware that it's possible you could have two different centers of intrusion and overprinting types of alteration. Yes, Frankie?
It's possible to have the lithocap when two stages of intrusion.
Well,
in which stage is development?
The lithocap only develops during the potassic stage. Remember, brine and vapor. Brine forms potassic, the vapor rises, condenses to form the lithocap.
Yeah, in the early stage.
In the early stage, but not during the Muscovite stage.
Yeah.
Because we don't separate brine from vapor. We only have the liquid causing Muscovite overprint, bringing copper. Yeah, so lithocaps form in the early stage. That's why we say that there must have been a lithocap, but very shallow.
That means if you have a lithocap, not necessarily you have in deeper part mineralization. Because the later stage is not possible, no exist.
We can say if lithocap, we know there was a brine at depth, and also potassium feldspar, biotite. But yes, lithocap alteration doesn't mean copper mineralization, but it's possible. The only answer is drilling. But hopefully drilling in the right place. Alteration zonation, okay, let's test here. Where do we test at Kimsikocha? Diatrema? Or is the diatreme on the margin? Maybe the porphyry is north. I'm not sure where the best place is. It's deeper, but where? Below Kimsikocha? Maybe not. Maybe north? Someplace, or yeah. So this is a good example of overprinting, not just evolving one system, but then a younger intrusion and overprinting. Okay. So
what with the Muscovite generated in the first stage when it's overprinting? The biotite is altered again into chloride.
yeah, it's typical. I say Muscovite, also chlorita. There's chlorita here, chloride Muscovite. Yeah. So the mafic biotite goes to chloride.
Yeah.
The potassium feldspar to muscovita. Yeah. Okay. So, this is the picture here of alteration. We go back to our model. This might be El Salvador. 1 kilometer lithocap, eroded. Only the white mica to peroxide transition. And 700 meters deep, like porphyry copper at El Salvador. Now, what about the sulfides? We'll look very quickly at 2 sulfides at Bingham and sulfides at El Salvador. Because at the surface, often sulfides are supergene oxidized. But not always, and in drill hole, we hopefully have sulfides present. So at Bingham first, the intrusion at depth. At depth, we have chalcopyrite bornite. Bornite digenite chalcopyrite. Very high grade. Then mucho chalcoprita con poco pirita. And then zone, más pirita, menos chalcoprita, más pirita. And distales, stalerita, tenentita. So very simple zonation. If we were mapping mucho pirita and then más chalcoprita, maybe right here, pirita chalcoprita, just an outcrop, let's drill. Of course, post-mineral tilting. So, but still, the zonation of sulfides will also help direct towards the middle of mineralization. At El Salvador, the same. Chalcoprita, bornita, magnetita at depth. Shallow, bornita, chalcoprita. No tiene magnetita. Lateral, chalcoprita, pirita. Más lateral, pirita con un poco chalcoprita. So these are all important observations. Don't just say pirita, chalcoprita, but the ratio, in Espanol, ratio, proportion. Yeah. Pirita 2, chalcoprita 1, 5-5, or 3-7. That's important. What is proportion? Because we see zonation in proportion. Okay? Pardon?
100, which was we had 0%
For now, yes. For now, you are out here. But where is the center? Now also look, shallow levels, pirita, chalcoprita, bonita, enargita. Now we have bonita con pirita y enargita. Enargita is alto sulfuration. And here, pirita, bonita, enargita at shallow levels. This is the potassic stage in gray. And then overprint, white mica, cerecita, and the dashed, the D veins. So here we have D vein, tenentita, and más arriba, enargita. So zonation, potassic, zonation in D veins. ¿Por qué tenentita evolving to enargita? We'll look at simple phase diagram to explain this zonation, okay? Next. Okay, this is amount of sulfur menos, más, temperatura, alto, baja. Very simple. Pyrrhotite, arsenopyrita, magnetita plus bonita. Low sulfidation. Just definition. Intermediate sulfidation is pyrita, chalcopyrita, tennantita is intermediate. Enargita is high sulfidation. Quimsicocha, high sulfidation deposit, mucho enargita. O pirita bonita. No es magnetita bonita. Pirita bonita is alto sulfidation, or pirita digenita, or covaline. So let's look. Constant temperature. We have very low menos sulfur. No tiene sulfuros, solamente ferro.
For example, in some veins there are some covaline. But the covaline is in the vein, is
Yeah?
in the veins.
Yeah, well, ¿dónde?
What happened?
¿Dónde?
In some veins.
¿Dónde?
I don't know what really you know.
Yeah. Well, it's, yeah, it's high sulfidation, or very high. Very high sulfidation. Well, we'll come back to that. Un momento. So, low sulfur, no sulfuros. Mucho sulfur, sulfur nativo. But intermediate sulfur concentrations, different assemblages. So one possibility is to change the sulfur, concentration of sulfur. What is the otro proceso for variation? Yeah. Does anybody argue?
Overprinting.
Pardon?
Maybe overprinting.
Overprinting, maybe, but what is the simple geological process? Cooling. We can start at high temperature, magnetita bonita, pyrite, pirita, chalcopyrita, enargita, just by cooling. And what happens when the fluid rises from deep to shallow? Cooling. So El Salvador, Bingham, deep bonita, then chalcopyrita, pirita, and at El Salvador, shallow, enargita, and pirita bonita. So, very simple, cooling. We start at the magma. This is composition of magmas, high temperature. Magmatic fluid, first is low sulfidation, magnetita bonita, in the deep core. As cooling goes to pirita, chalcopyrita, maybe con magnetita, hematita, specularite. That transition is in the middle of pyrite, chalcopyrite. Okay?
So, for example, if I have a covaline or is maybe close porphyry system, could be?
It's possible. Yeah. A huge discovery in Indonesia, not public yet, is 90% covaline. So, but mostly porphyries are in this area. Why do we see base metal veins in porphyries? Because we have wall rock buffer. iron in the wall rock. At low temperatures, the fluids are reacting with the wall rock, and the fluids change their evolution path as they're cooling because of this wall rock buffer. Chlorite, magnetita, chlorita, whatever.
What is buffer?
Well, you know a buffer, pH buffer. Well, from chemistry, in I don't know the front,
I don't know the
Franco or
I don't know the name.
well,
Buffer.
buffer
What's the buffer?
in español.
El buffer es
Yeah,
como una abertura, una ventana.
yeah. But in your chemistry class, you titrated one chemical into another chemical, and there was a large buffer that, yeah, maybe better to find the French for it, then you'll understand. The buffer is something that controls the stability. Because in wall rock it has a lot of iron, biotite, chlorita, etc. Do you see it? But what rocks have no iron in? No tiene ferro and remember?
Buffer is like influence in some.
Yeah, influence, strong influence. So this is causing reaction. But do you have in front? Tampo, okay. You remember high school chemistry? The pH buffer, you were titrating some little experiments, and it's simple. Well, here, huge buffer, wall rock. Now, where do we not have wall rock buffer? What is residual quartz? No tiene ferro. Remember White Island, Satsuma-Ujima. The iron is flowing into the ocean. We're left with silica residual, silica buggy. There's no iron, so no buffer. So cooling of this fluid in the lithocap to the base of the lithocap, it enters the lithocap. No iron, no buffer, so moves into enargite stability. That is why the silica buggy has enargite, because there's no wall rock buffer there. Very, very simple. Not magic, not complicated. But also quartzite, sandstone, or quartz veins. So a large Peruvian high sulfidation deposit is hosted by sandstones. Sandstones are the same as residual quartz. So that is how we get enargite or, Julie? Covaline. But also in large quartz veins. Large quartz veins, solamente quartz. Maybe iron buffer in the wall rock, but in the quartz vein, only chalcopyrite. So the D veins at El Salvador, tenantite, tenentita, más arriba, energita, cooling in a big quartz vein. That's the simple answer. Cooling is most important. Cooling was important for silicate zonation, alteration zonation. Cooling is also important for zonation of sulfurous. Some additional factors, but that's the fundamental. Controlling the zonation, because for exploration, we want to look for zonation patterns. So collect samples, record the mineralogy, plot the results, look for zonation patterns, find the middle, drill.
example,
We say not rocket science, it's simple.
for example, in the case, for example, for cover-line and chalcopyrite, could be 2 stages.
It might be 2 stages. We might have chalcopyrite and then later stage covaline, ruling. Yeah.
Because, for example, in those days, I said, is in some places you cannot see very well cover-line, for example. But
Yeah.
in some places you can see very well cover-line.
Yeah, maybe late veins, cooler veins. Yeah. So, of course, case by case, but this is the framework for interpretation of observations. Okay. Pardon?
No, solo, just to say,
Sí.
solo para decir que en la visión de los diferentes fases de inclusivo, de las donaciones, de la geoquímica, de las donaciones, de la interacción, también es importante usar la lupa, otra vez, usar la lupa para identificar qué son los sulfuros que tenemos. De momento, a partir de la pirita no tenemos otros sulfuros, pero espero que pronto vamos a tener sulfuros diferentes de cobre y será importante aunque en el campo, yo por ejemplo, a veces identificar 2 tipos de sulfuro diferentes, estoy muy bueno en eso, pero si no sé, yo vuelvo aquí, le enseño a Robert y Robert me dice qué es, o a Osvaldo o Julie. Entonces, cuando se ve diferentes tipos de minerales en el campo, coge la muestra, aunque no está muy mineralizada y que no le vamos a mandar al laboratorio. Es solo porque veis algo diferente. Y otra vez, cada cosa diferente o cada cosa que no entendéis, lo coges y tenemos que siempre tener un tiempo para cada geólogo junior para revisar con un geólogo senior. Y tenéis que preguntar, oye, yo vi eso y no entiendo lo que es, o me parece diferente, me parece que es eso, ¿estás de acuerdo?
What happened, for example, for the galena and the
Galena. Well, galena does not plot on this. That's a different, it's a lead. But sphalerita, if we have marmatita is iron-rich sphalerite, very low sulfidation state. Whereas iron poor sphalerite, remember zinc sulfur, but iron can replace zinc, but zinc is 2+, so only iron 2+ can replace zinc 2+. Iron 2+ is reduced. If we have more oxidized system, then iron is 3+, and it will not replace sphalerite. So more oxidized conditions, we have low iron sphalerite. And we can also contour this in terms of iron in sphalerite. But we're not going to use high technology to analyze it. Question is it meal or yellow or meal color of sphalerite? Low iron. Is it, black? Marmatite, high iron. So sphalerite is usually intermediate sulfidation. It's not high, but it's intermediate to even low. I'll give you the paper that describes all of the details. Okay? Yes?
There are a sample with only chalcopyrite, no pyrite.
Yeah.
Only chalcopyrite. What means?
Well, usually calcoprito solvente is más proxima. We, for example, For example, we have, usually only calcopyrite. There's sometimes bonita there, but other times I see solamente calcoprita. This is more close to low sulfidation. But once we get into intermediate, then we start getting pyrite. Definitely, if you see only calcoprita, I think that's more proximal than calcoprita con pirita. That starts to become lower temperature, more distant. Okay. So, early, deep, high temperature. Silito, and I've changed this, he thinks longer time. But this is for a district. But for individual deposit, it is shorter time. So early, deep, high temperature, we have potassic alteration with calcopyrite bornite. On the margin, just propylitic. As we cool, both alteration and sulfides evolve to shallower, later, and lower temperature. This is a general concept. So remember, early potassic, we have deep brine hypersaline liquid and vapor separation. The vapor separates or condenses and starts to form the lithocap. Okay? But in the early stages, it's only pyrite. Sin, oro, plata. Cobre. Barren. At this stage. Lithocap is barren. Maybe copper in the deep levels. Then cooling of the system, we go through chlorite sericite with calcopyrite pyrite. This is the lower salinity liquid, and it may then rise to the level of the lithocap with metals. But as it cools into the lithocap, we, instead of calcopyrite pyrite, intermediate sulfidation, we get high sulfidation. Pyrite enargite, pyrite cobalite. Continued cooling, we just get white mica overprint, including pyrite chalcopyrite, even pyrite bornite or enargite. These are high sulfidation, and that's because there's no iron in sericite. So we also have lost the rock buffer. In the latest white mica only stage. And in that sericitic, we can continue to cool to peroxide stability. So increase of acidity and sulfidation state is due to cooling with time. That's the main driver. Now this is simple, a single intrusion. What if we have multiple intrusions? Then we have possibility of overprint. More complicated. Muy complicado. So I'm only looking at the simple example to understand first. And then, what happens if we have quartz alunite deep into the system? Well, as I showed at El Salvador, this is 38 million years. This is 42 million years. This is actually, that overprint, deep overprint, is due to a later intrusion. And that is how the new deposit at Escondida was found. The quartz alunite overprint of Escondida is actually related to Escondida Este, deeper, larger and higher grade than Escondida. So when you find evidence for completely different alteration, it may mean there's even a younger and deeper intrusion. The district. Sorry, Huli.
In this speech, could be there something like copper, native copper?
Native copper can, because native copper is very high sulfidation. So it's possible to have native copper in this state or even up here. Do you ever see native copper? Okay, this is Salar Norte, recent discovery in Chile, and beautiful steam-heated alteration. Present here, drilling now a dome. They cite domo de Indecita, 600 muestras, suelos, menos 29 ppb. So this is steam-heated alteration, nada oro, but still ore deposit. 150 meters abajo. So we'll come on to this in our discussion, the details, but it has an alteration style, steam-heated alteration, that's important. Some people call this steam-heated alteration advanced argillic. Also, the supergene alteration is called advanced argillic. And the hypogene quartz alunite is advanced argillic. And on a map, I see people only printing advanced argillic. What is the minerals? What do they mean? Is superhenica or steam heated or hypogene? So this short lecture will be discuss there are 5 environments of formation of advanced argillic minerals. So no more advanced argillic, please. Name only mineralogy and environments. It's important. So in this second lecture, we'll look at active systems and how the term advanced argillic is used. Advanced argillic minerals form in 5 different environments. Then, after this afternoon, we'll look at veins. And when we have time, we'll discuss lithocaps, relation to porphyry centers, Kimsikocha type enargite gold, and also carbonate replacement. Okay? So these are the still 3 lectures. For now, just background on advanced argillic, because advanced argillic is very important. It's very near the surface commonly, much of it. So importantly, describe observations, avoid models and names. EPITERMALES, this is muy famosa. Valdemar Lindgren, Swede, studied at Freiburg in Germany, went in 87, at the age of 27, went to the Wild West of the US and started mapping. And he came up with the term epithermal in 1922. He is the grandfather of modern economic geology. There are also some Europeans about the same time, but basically he wrote a book that's still useful. Epithermal, in Greek, epi means over or above. And he said less than 1 kilometer deep. For high sulfidation, like Kimsikocha deposits, Kimsikocha is not here, but we can see large vertical intervals and maybe 200 to 300 meters below the surface forming. Same with intermediate sulfidation veins, potentially large vertical intervals of several hundred meters and deep. These are forming arcs. By contrast, low sulfidation deposits formed in rifts, zones of extension, tend to have smaller vertical intervals and closer to the surface up here. So that's important to understand the tectonic setting and the potential depth. First of all, where is the paleosurface? And also, what's the potential depth to the top of mineralization? Should we be drilling 100 meters or 300 meters? You could drill only 100 meters and say nada. Next company comes 300 meters deep, an ore body, just like Newmont and IAMGOLD. We'll discuss Newmont drilling 100 meters deep over the top of Kimsacocha, Loma Larga. Richard Spencer, Julie, Franklin. They said, no, 300 meters. And they discovered the deposit. So this concept of depth is important. Muy importante. Okay, and we can establish paleo depth from minerals, mineralogy, including clay minerals. Okay. So if the erosion is 200, 300, 500 meters, probably the veins are exposed. We can map the veins, sample them, okay? Relatively easy. If the area is eroded to nearly 1 kilometer, probably most epithermal potential is eroded. Maybe there's some deeper, locally deeper, but most is erosion. So we need to know, again, based on mineralogy, how deep, how high temperature are the minerals, and therefore depth, how deep. When we have less than 100 meters of erosion, then we know all of the potential is below the feet. And at particularly Yowie and other places with silica, sinter, and fossil reeds growing, paleosurface. Part of Yowie must be right here. Then the question is, where to drill and how deep to drill.
Yeah.
So it's still jobs for geologists, not just geophysics. Yeah. So, okay, this is Silto's model for alteration. Potassic, white mica overprint, lithocap. The ore environment, porphyry. He calls porphyry copper system, but not only porphyry, but also the lithocap, potential proximal epithermal alto sulfidation, marginal intermediate sulfidation veins, deep enargite lodes, skarn and limestone replacement, carbonate replacement, mass distal, even sediment disseminated gold. Some people, including Silto, argues that this is Carlin. Carlin is distal porphyry associated with carbonates. Much argument, but he may be right. So this is the ore environment. Next. Now this is epithermal, más o menos 1 kilometer. And what about these 5 environments of advanced argillic? What does advanced argillic mean? Meyer and Hemley defined it in 1967, aluminosilicates, ionita, diquita, luisita, periphelita, andalusite. Also, the fluorine, zunite, and topaz. Diaspore, which is aluminum oxide, not silicate. Do you have? Yeah, it's there, okay. Plus, elenita, or APS, aluminum phosphate sulfate, and anhydrite. So this is the advanced argillic group. Silica vuggi, silica residual, in fact is not advanced argillic, but it's closely associated with advanced argillic. Basically, even aluminum, lixiviation, aluminum. Okay. High temperature to low temperature. Like at, this is my alarm clock at home. I actually have a rooster. Yeah. Sunday I thought, oh, did I forget to turn it off? Like at El Salvador, cooling of magmatic fluid, transition white mica to perovskite. This is advanced argillic. Hypogene, acid sulfate chloride, in lithocat, residual quartz, and alunite kaolinite. In feeder zones, perovskite dictite. Later, talking about veins, we have carbonic acid. Anybody consider cerveza? No, not yet? What's the pH? ¿Cuántos pH cerveza? Más o menos. Psh. Psh. What's the psh?
Yes, it's CO2.
CO2. Bubbles. Burping. I can't burp. What's the pH? 4.5. It's relatively acidic because of carbonic acid. CO2 in solution, carbonic acid. And that forms elita, smectita, but also mas kilonita. Kilonita is advanced argillic. Steam heated acid sulfate at the paleogrometer table. Kilonita, elenita, advanced argillic. Suprahenica, kilonita, elenita, iron hydroxides, advanced argillic. So 5 environments of advanced argillic minerals. So if we only map advanced argillic, it could be 1, 2, 3 different minerals. We need to map out the mineral assemblages. So first describe with lupe, and then get support if necessary. Yeah, almost all these minerals can be identified. Sometimes perovskite, it's useful to get distinction. But once you have 10 samples with perovskite, 10 samples with illite defined, few with diaspore, defined by Franklin, then you can use those as a library to say, ah, yeah, perovskite looks different from illita. Yeah. So for each prospect, if you end up with different groups of minerals defined, build boxes and keep those as libraries for new geologists visiting or something. These are our alteration minerals.
Can you? ¿Puedes hacer eso?
Yeah.
Entonces, cuando tú
The next
cruzas muestras bonitas que donde se una colección para que podamos revisar y
For training.
sí.
It's very useful to help. Okay, I can see the difference. Yeah, Elita, I can see the difference. And then you can map with Henlins, and 70-80% of the time be correct. You still want to check some things with shortwave infrared, but it's not necessary to be going in the field with like the halo. They just go and they don't even look at the rocks, just point the halo gun at the rock, and then read a mineral. But this is only computer software. The eye is better. Lupe and the geologist is better. Más mejor. Okay, so that's the background. These mean events are geologic. So we go back to our environment, cooling of magmatic fluid, white mica porphyry, El Salvador, top of the porphyry. It's important if you find this type of porphyry because it tells you you're very close to the porphyry. Here, hypogene. This is relatively shallow. Steam heated around the margins of intermittent sulfidation veins. Steam heated acid sulfate over the top, potentially over the top. And late post-mineral supergene oxidation of pyrite. So define the minerals, the textures, the morphology, as we're going to review, and then map out each of these potential types. And the reason I started with Salares Norte, there is all three of these environments are important at Salares Norte. If we just mapped advanced argillic, we wouldn't have any proper zonation. Okay? Okay, the first was actually number 2. We discussed it before, SO2, HCl, and other gases. Well, there is the cooling of magmatic liquid, but I cannot illustrate that with active examples. That's 1 kilometer deep. But we saw at El Salvador this transition, white mica to porphyry. But vapor condensation, lithocap alteration, residual quartz. This is due to SO2, magmatic vapor, plus water, disproportioning to sulfuric acid. So we have sulfuric acid and HCl from magmatic vapor. At high temperatures, these acids are associated. Associado? But on cooling, as we cool, we get more and more dissociation. So cooling leads to dissociation, which causes increased reactivity. At high temperature, 300 degrees, we have these features. At 200 degrees, dissociation, we have a lot of hydrogen. And it's the hydrogen ion that's responsible for alteration. That's by definition, pH. Remember, definition of pH? Minus log activity of hydrogen ion. Okay, but basically, that is pH. More hydrogen ion, lower pH. Lower pH, more reactive. Very simple. Okay. White island. For example, here in the crater, this is unfortunately where the people just yesterday morning were killed. And here they're walking in this inner crater, and there apparently was an eruption. If you erupt 0.2 waters at 70 degrees Celsius, and you were hit by that, muy peligroso. Yeah. In retrospect, maybe shouldn't have been there. As I said, fluid flows out, lixiviation, this is dissolved andesite. Iron, aluminum, sodium, potassium, calcium. And that's what forms residual quartz. Is this originally the SO2 and HCl? Now, it's the vapors are condensed by the rainwater, but the vapors still are present there because we know such an acid pH. And in that lake, the lake goes up and down. In the lake, this is pH 0.2. As it's drained down, there's silica colloidal. Here it is mud cracking because it's drying out. Why is this important? Silica colloidal, muy fino, laminations. Well, here, Volcan Puas, Costa Rica. It's similar. pH 0.5. Silica colloidal, that's the blue-green or gray color of the lake due to colloidal silica in suspension. If we look at the margin here, there are fine laminations of silica colloidal, but then also blocks, plastic blocks falling in and deformation. But the blocks are from the wall. The silica colloidal is from the lake, the acid lake, filling the crater. Again, why is this important? Let's look at Yanacocha in Peru, the largest high sulfidation district in the world. 38 millones onsaladas? Yeah, oro. over 1,000 tons, 1,100 tons of gold produced. This is a dacite dome, Domo de Cita Chaquicocha. We can see vertical flow banding. It's a dome. Right on the margin, right here, find muy fino laminations going cross-bedding. In Espanol, cross-bedding? Yeah. Where do we see cross-bedding? Sublacustrine. Yeah, lacustrine. So there was fine laminations here, but cross-bedded. Tells us that this is not replacement. Muy fino laminations, no replacement textures. Fine deposits of silica. This whole body is residual quartz, sterile, but on the margins, these sediments. That tells us that there was an acid crater lake present here. Therefore, this is paleosurface. This is the sinter equivalent of the lithocap environment. We do not form sinters in acid lithocap environments. ¿Por qué? Because at acid pH, silica tetrahedra does not polymerize, does not grow. So sinters only form in neutral pH, pH 7, 6, 7, 8. pH 1, no any sinter. But we can have laminated lacustrine deposits of silica colloidal, which is also indicating paleosurface. So if you see anything like this, definitely describe it. It tells you something. This is paleosurface. Elsewhere, muy fino, silica colloidal and con clastos. So at times, clastic material washing in. Even in drill core, muy fino laminations. These are lacustrine sediments, but solamente silica colloidal. So, vapor condensation forms this alteration. Through these reactions, we produce these very low pH acid springs that's leaching the rhyolite dome here. Now, Satsuma-jima is right there, 20 kilometers south of Kyushu, Upon Alasur, Upon Alasur, Kyushu. So Satsuma-jima is active now. On shore, there are Iwato high sulfidation deposits, 3 million years in age. This is quartz elenita, a breccia, cemented by quartz elenite. In the pit, this is all silica residual, silica vuggy, with supergene oxidation. So all the brown is iron hydroxides because of supergene oxidation. But on the margins, here's silica residual, quartz elenita. We know the pH is 1 to form silica residual because we need low pH for aluminum lixiviation. At pH 2, 3, 4, aluminum stable in elenita or kelinita. But at pH 1, even elenite is soluble. Solubile? Yeah. So this is simply recording the pH. The different minerals recording the paleo pH, pH. And importance is that the residual quartz is the host to subsequent gold. So the same process occurring today, Satsuma-jima, was occurring here 3 million years ago, 20 kilometers distant. So, by looking at active volcanoes, their vapor condensates, the compositions, we can understand the alteration.
Sorry,
Pardon?
this picture, the guy,
See?
the alumina is dissolved where the pH is lower, is kind of one.
Yeah, originally, these are large bodies, like here, 100 meters across. Originally, at the start, there would be residual quartz, quartz elenita, but mas liquidos acidos, then progressively going out, mas lixiviation. So elenite dissolves and precipitates further out as the acid fluids react with the rock. Still, these are pequeña, about 10-20 toneladas de oro. Whereas at Yanacocha, the bodies are muy grande. So very much more acid liquid coming through to leach to make the larger bodies. Okay, that was our hypogene acid potentially forming residual quartz. Now, steam heated near surface. H2S oxidizing to sulfuric acid. This oxidation in the zona verdosa, or in Ecuador, in Espanol, unsaturated zone, zona verdosa, the groundwater table, surface, groundwater table, unsaturated zone. So we can have atmospheric oxygen circulating. Oxygen does not circulate below the groundwater table. So we're in the unsaturated zone between groundwater table and surface. Well, back to White Island. We have high temperature fumaroles, SO2HCl, but here on the margins, low temperature vapors, solamente CO2 and H2S, no tiene SO2HCl. So here, a different environment, we can form H2S oxidation. Well, let's go to La Coipa, Chile. This is a lithocap hosted silver gold deposit in Oita, Oro. And this is residual quartz. But right here, over the top, is a zone of elenita, keolinita, muy friable. And on chalcedony, so it's sitting over the residual quartz, and this is sterile. Con oro, silica residual, steam heated, sterile. It's looking like this. Oh no, this is residual quartz, gold ore, even with native sulfur. But here, the chalcedony blanket, you can see it's chalcedony, even opal, with fractura conchoidal. Conchoidal fractures, low temperature silica. Well, 4 kilometers to the north of La Coipa, Puren was an area of steam heated alteration, keolinita, elenita, a horizon. And this area was tested, dose perforations, and no mineralization, but continued exploring to north, at Puren Norte, below the steam heated alteration, made a discovery. This right here is Puren Sur, steam heated alteration, and that right there is the paleo groundwater table. That's a chalcedony blanket. The chalcedony silica replacement is muy dura, very resistant to erosion. Well, to the north, Puren Norte, this is silicification, Yelita. This is sitting below a blanket of steam heated alteration. This was discovered below a barren blanket. This blanket has maximum 3 ppm plata. But it's anomalous because outside this area, 0.1 ppm plata. And that's where the ore body is, with about 60 grams silver and 1 gram oro. Now, open pit, and we see this is the zone of steam heated alteration. So you can see very flat-lying bleached kilnite zone. That would be the paleo groundwater table, right through there at the base, and this is the zone of steam heated alteration kilnite. Essentially sterile. Why? Because low temperature vapors do not transport oro, plata, arsenico, and ammonia. Solamente mercurio. Mercury is very volatile. You can get mercury anomalies, but no others. Pardon?
How they recognize the environment in those two places?
Yeah, well, it was recognized that this was, well, first of all, over La Coipa Norte, there is the sterile steam heated alteration, muy friable, quelnita, más o menos elenita. And at the base, chalcedony, opaline. This opal replacement at the paleogroundwater table. So here we have the, let's see, this sample is from right there. And right there is this. And see, groundwater tables are usually flat. And here we see the chalcedony silicification is nice and flat. So, this also, muy friable, quelnita, elenita, it's a blanket. Blanket, what is a blanket you put on a bed? Sabana. So, this is just a blanket. And the blanket of alteration is limited by the paleogroundwater table, which is defined by opal, chalcedony. See? The blue is the steam alteration, basically a horizon, a blanket. So, mineralogy, quelnita, textura, friable, con opal at the base, flat-lying blanket, mineralogy, textures, morphology. It all supports.
For example, in the soil target,
Yeah.
they really, but
Well, those say perforations. Did they drill in the right place? I don't know. But for whatever reason, this was distal. But they continued to follow to the north. In the north, there was still steam heated blanket alteration.
yeah, my question also is,
Oh.
so the
How-
fluids coming from the north part to the south.
It's possible, or they simply didn't drill in the right place. This could be another upflow. Now, they used also geophysics. They were also analyzing talus fines, or soils. And as I said, very low anomalies, but the steam heated alteration, punto uno, plata, background, threshold. But in this area, 1 gram plata, maximum 3 grams. 3.1 was the maximum over here. So that was encouraging. Very supple, but still encouraging. Oro, nada. And that was only, what? I don't know, 50, 42, 50, 250 meters. So that's about 75 meters vertical.
How is the section of the northeast?
Section 1050 northeast. So the sections, we're looking north.
Okay.
So section sort of northeast through here. Okay? If you want, I can give you this presentation. This was Geologic Society in Nevada by Antonio Rivas. At this time, he was chief geologist of Newmont. Or before that, Placidome. Maybe still Placidome. Yeah, Placidome, because this La Coipa was owned by Placidome. Yeah.
Can you explain again how is forming so the chalcedonic blanket and the heat steam zone?
Well, let's go maybe to, that was arc environment, but now here, this is Nevada. This is a low sulfidation environment. Silica sinter over here to the north, but this area, steam-heated alteration, large fractures with elenita. They call it sulfur because of sulfur nativo being worked here. And I was working here with another geologist a long time ago. This was 1982, 1982 photo. Sulfur nativo, cinnabar, mercurial. And subsequently, companies drilled this area. They didn't drill right at the center. They drilled it here. This is what it looks like now. Production of más o menos 100 toneladas oro below the steam-heated zone. And here are these two pits below the area, and this to the north, the area of silica sinter. Lateral, probably because of hydraulic gradient. So here we see, again, just like Puren, Norte, we see the very thick but blanket-like and sharp base of the steam-heated zone. So the formation here, we have a quartz vein with adulary calcite and gold. And liquid rising, it was boiling as it was rising, so the vapor ascended vertically. Above the groundwater tables, the vapor condensed in the vadose zone, zona vadosa, and the H2S. H2S is a gas in solution in the liquid, deep liquid. But when the boiling starts, the H2S is volatile, like mercury. So it fractionates. It's transported into the vapor. And so it rises. Have you ever been to a geothermal area? Even in here, sometimes you can smell rotten eggs.
Yeah.
That's H2S, of course. That's coming by the vapor. Now, if some of the vapor condenses, the H2S goes back into solution. The oxygen comes from the atmosphere, and we produce, again, sulfuric acid, but not a pH of 1 or less. Here, the pH usually about 2.5. So still, keelnite is stable. There's the groundwater table. Any silica that goes into solution in the condensate comes down to the groundwater table and it flows off along the Taylor groundwater table. Why is silica present there? Well, this steam-heated zone must be an aquifer. What is a good aquifer? Maybe a airfall tooth. What's a volcanic tooth made of? A lot of volcanic ash, which is glass. Very easy for this solution to dissolve that glass, which is 70% silica. The silica is in solution. As it cools, the silica precipitates. Maximum temperature, 100 degrees. Because boiling point at surface is 100 degrees, so that's maximum temperature. So as we go along here, it's probably low temperature, 40, 50 degrees. The silica in solution then silicifies, replaces that horizon. And we get that opaline, very low temperature opaline replacement of the tooth. When we look at that chalcedony or opal, oftentimes we can see the original tooth texture. Sometimes we can see glass shards, muy fino cristales, and sometimes even lithics.
I saw that yesterday.
Yeah, well,
Something. But remember where?
you have to imagine it, but this is a tooth. This opal, you can actually see a little bit in that texture, muy fino cristales. This is a tooth, and that tooth was the aquifer for the outflow down the hydraulic gradient in that tooth, and then the silicification, opal, replacement of the tooth.
This opal would be similar to the opal for phase 2.
Maybe very late opal, at low temperature. Opal forms at low temperature. It's mucho agua, silica con agua. With time, crystallization, the water is lost, and we get cryptocrystalline chalcedony, sin agua. So the difference between chalcedony and opal is opal mucho agua. Chalcedony muy fino cristales, like opal, but sin agua. Yeah.
Pero, perdón, depende del pH del agua o no?
Well, here, this, the pH, well, go ahead. The acidification of, or oxidation of H2S to sulfuric acid, pH más o menos 2.5 a 3. And 2.5 a 3 is kelinita, stability. Más alta pH 5, then elita. Más baja 1, silica residual. Kelinita no es stable. Solamente silica residual, very low. So it's important. pH 1, pH 3, pH 5.
Example is common to find silica or vanilla lower level.
Yeah, silica vagi, menos 2. It's más o menos pH 1. Yeah, we saw at Satsuma Iwajima pH 1.1 hot springs. At White Island, menos pH 1, 0.2. Costa Rica, Volcampoas, 0.5. So at that pH, complete liquidation. Solamente residual silica. Residual silica in solution is present as silicic acid, H4SO4. So pH 1 or pH 7 does not affect the solubility of silica. It does affect the solubility of alumina, iron, etc. But silica does not dissolve in acid solutions. That's why we have silica residual, silica vagi, because it's not soluble. We'll be coming back to this when we look at different environments and the pH stability of different minerals. This is sort of an introduction. Well, this is Southern Latin America. I have to have the happy face, otherwise, at least in Southern Latin America, they would know the geologist, and if they knew the geologist was working here, then this is a secret area. But here we are at 5,000 meters, 5,000 meters. That is about 100 meters más arriba, and that is a young geologist right there, climbing up. Here, the cameraman is an old geologist, standing here, and then this young geologist collects samples, he comes back, and this is what he found. Chalcedony and muy variable kelinita. And not only here, there, and there. Chalcedony defining the paleo groundwater table. Maybe we were at the 4,900 meters here. But young geologists went up very fast, in fact. And we knew really what it was, because a large block here rolling down. So that defines, that was the paleo groundwater table. This area, actually an eroded stratovolcano. And nearby, at an adjacent prospect, 10 kilometers away, shallow drilling through de cita. We can see the cristales de quartz, steam heated kelnite. And at the base, chalcedony replacement. And in other drill holes, brecciated chalcedony. Here also, brecciated chalcedony con opal. And this is not wet. You know, sometimes opal is so opaline, it's shiny. So if you have just a sample of opal, no say, but in several places at the same elevation, you say, aha. Maybe, and it's replacement, clear replacement. You can see here the más o menos, maybe a tooth, lithic crystal tooth. If it's replacement, then definitely it is defining paleo groundwater table. Even if the kelnita is eroded. Muy variable, muy dura. So it's easy to erode the kelnite, but maintain the horizon chalcedony. Well, I think they look like almost finished. And that is the steam heated environment. We'll come back and look at examples of steam heated alteration in other lectures. Bien? Buenas tardes. ¿Está bien?
La comida está aquí. Sí. Podemos ir.
Just to finish up the last two environments of advanced argillic alteration generation, we looked at steam heated, and of course that's for the zone above paleo groundwater table, generating kaolite, alunite, and also opal replacement at the groundwater table. But there's also another environment below the groundwater table that's CO2 rich. And remember, CO2 is sufficiently acid due to carbonic acid. We'll come back to this later this afternoon, but just to mention, here in New Zealand, this is the volcanic arc andesites to the east, and to the west is back arc extension zone, rift margin, with a geothermal system called Broadlands right in through here. Waitapu that we will look at is over here. At the surface, neutral pH liquids, vents, including silica sinter, present, but these are wells discharging from the deep system. So we'll look at a cross section through here, and you can see these are up to 2 kilometer deep geothermal wells, and the dots are samples collected. And these isotherms are measured temperatures. So we know exactly the temperatures of these zones. Clearly, in this area, there's a deep upflow. So liquid is rising in this area. It starts to boil. And as it boils, it loses vapor. Now the boiled liquid can rise through fractures, discharge from hot springs. Also, the vapor related to this boiling can rise and form steam-heated acid sulfate blankets above the paleogrometer table. But there's a lot of vapor that never reaches the surface. And some of this vapor condenses on the margin of the system, below the paleogrometer table. Therefore, the H2S does not oxidize. There's no oxygen. In Espanol, oxygen is oxígeno. Nada. Solamente en zona de V2. Here, no oxígeno. Therefore, we just get carbonic acid-rich warm waters. This well discharges CO2-rich bubbling, just like opening a beer can. And this just is bubbling. It's not discharging high temperatures like these wells. So we can see, we'll come back to this later. We see in the upflow, there's illite alteration. On the margins, there's lower temperature, illite smectite, but also this CO2-rich condensate, pH 4 to 5, smectite, also kelnite and carbonates. This is the extent of kelnite in places several hundred meters deep. So we can call this also advanced argillic alteration because of kelnite. And yet it's different from the kelnite in the steam heated zone, pH 2 to 3. And also there is siderite, iron carbonate. So we'll come back to this when we're talking about veins, but it's very common to have illite, smectite, kelnite in halos. And now we can see why. Because of the CO2-rich condensate. If you took your beer and heated it to 150 degrees and put K feldspar in 150 degree beer, cerveza, you would form kelnite. So maybe sometime you can do experiment with your bottle of beer. Put some feldspar in and heat it to 150 degrees. But you have to seal it very hard to keep it from boiling away. Okay. So as I say, we'll come back here, but this is another fourth environment of kelnite, advanced argillic alteration formation. Finally, post-mineral weathering, supergene weathering of pyrite. Pyrite oxidizing, again in the Vadose zone, forming sulfuric acid, but iron hydroxides. And so the alteration here is very red because of the iron hydroxide. And the alunite often filling fractures. I do not know much about supergene oxidation, but it's very important to economics of a development. Because if we have mucho pirita, it's normal refractory. We refractor already. The gold is in the sulfide, and you have to process it. But if supergene oxidized, then the gold is free. Let's see about restarting this. Let's see. There we go. That's a little bit better. And this alunite is very blocky, but it's crystalline, but only 2 to 4 microns. So impossible to see with a hand lens. So very blocky, often in veins, and with iron hydroxides present. As I'm going to show, like at Salares Norte, there's supergene kaolinite overprinting steam heated kaolinite, overprinting hypogene kaolinite. 3 different types of kaolinite. So we must describe the different types.
And how to
Pardon?
how to distinguish? That's the problem.
Well,
Here-
tomorrow morning I'll discuss hypogene alunite. Hypogene alunite is always crystalline. I always see it with hand lens. Steam heated alunite is never crystalline. Then you can recognize some with hand lens, but also then perhaps with confirmation from Franklin. Supergene kaolinite also, Rufino cristales. But in that case, there will be iron hydroxides. Also, the morphology. Do we have a blanket? You know, if we only have one sample, it may be difficult. But if we start getting 3, 4 samples, and they're limited to one horizon, then that tells us Paleovedosome, either steam heated or supergene. Then, if the alunite is with pyrite, alunite kaolinite with pyrite, it cannot be supergene. It must be steam heated. But if all of the pyrite is oxidized, it's still a blanket, then it's possible that it is supergene. So we have to look at the texture, mineralogy, and morphology. So, so we'll be coming back to each one of these environments, but at the start I wanted to show a overview. As we look at these environments in more detail, we'll see some of the textures and morphology.
Here the difficulty is that said that the weather alteration in surface here is so strong that all the rock that you see in the surface, most of the time they are oxidized, including when you rock them, they are oxidized. So you see maybe highlight on it, but how you will reconcile?
Yeah, that's a problem. It's difficult. Then that's why you pay your geologist a salary for him to work harder to think. So always look at the texture of the rock and think about the likelihood that there is supergene overprint, and then look for the underlying alteration. Do you have a mixture of maybe pyrite is gone, iron oxides, you have kaolinite, but you also have illite. Is the illite hydrothermal and the kaolinite supergene? At least you can have some ideas. And then, as I said, the morphology, etc. Get as much information. But it's not easy. In some places, the more supergene you have, but you still need to look through the supergene. Supergene is important in terms of mineral processing, but in terms of zonation, it's not so important. At the early stage, exploration, you have to look through the supergene overprint. And sometimes it's only a few meters or a few tens of meters deep. But also I saw quite a bit of sulfide in the various rocks looked at yesterday. So there's places of no strong overprint. So supergene oxidation of refractory pyrite is critical to economics, but that's further down the line. And more than just a few meters, tens of meters deep. It has to be the whole ore body. Like in Peru and Chile, very common. Here, painting of Yellowstone, of the Grand Canyon of Yellowstone National Park. And as I showed yesterday, the steam-heated kaolinite is up here, the chalcedony horizons, silica sinter, and yet now the silica sinter is down here. So we get steam-heated alteration, overprint in this area of kaolinite, opal up here. And down here, there's illite pyrite, which has been supergene oxidized. And it's difficult, but when we spent a day here, we could see the evidence for various, like the pyrite, illite pyrite. That's hypogene. But then clearly the kaolinite and iron oxides, supergene. The red colors are because of the supergene oxidation. If no supergene, this valley would be completely white. So, it's all important. So these are our hypogene vapor condensates, the cooling of muscovite, graphite, 2 steam heated, and then the post-mineral supergene. And that's why I argue that it's better to avoid a name like advanced argillic and report the mineralogy, the texture, morphology. Recognizing sometimes we can have 1 or 2 overprints. Okay? ¿Preguntas?
Yo no la entendí bien donde estaba describiendo los 3. ¿Puede hacer el resto de presentación?
Las 3 diferentes alteraciones que hay.
O sea, la penúltima no la entendí bien, esa explicación que dio.
Hablo más fácil porque no entendí.
Presentation.
La última. Sí. La última con diferentes. Okay.
Which?
Can you repeat the explanation for the canyon in
Yeah. Remember yesterday we looked at a few more slides and otra? ¿Dónde?
Esa.
Oh, okay. Well, this was radicular, is vuggy quartz, silica vuggy, con oro, and anahita. But then the silica vuggy, the pyrite, was supergene oxidized.
We'll speak out.
Sí.
I will
Sí,
explain
yeah,
in
sí.
español.
Yep.
Aquí tenías un depósito de oro. Al origen, este depósito era con pirita y oro y con cuarzo. Ahí hubo una alteración supergénica, es decir, una alteración con el tiempo y la lluvia que transformó la roca en arcillas y al mismo tiempo que ha transformado la piedrita, que es un sulfuro, en óxidos de hierro. Por eso es rojo, así, como cuando un trozo de hierro se oxida. Y lo interesante en este caso, y eso ocurre en varios depósitos en el mundo, es que cuando se destruye la piedrita, también se libera el oro que está dentro de la piedrita. Y los sulfuros ya se fueron, y es más económico tener este tipo de yacimiento, porque el proceso para sacar el oro es mucho más fácil. No vas a tener sulfuros, entonces a la salida de la mina no vas a tener aguas ácidas. Entonces es una cosa muy importante también, una vez que identificas mineralización o potencial mineralización, este tipo de alteración supergénica puede ser un avantaje muy importante para la explotación minera. Por ejemplo, en un proyecto que he trabajado yo de oro, que no era oro epitermales, pero mesotermales, ahí había una zona de alteración supergénica así, de más de 400 metros. Y toda la zona era muy rica, la mineralización era oro dentro de arsenopirita, y había muchas arsenopiritas. Pero toda la parte superior era totalmente alterada con la lluvia meteorológica, y todo transformada, la roca transformada en arcillas. Todos los sulfuros habían desaparecido, entonces el oro era libre. Y además, otra cosa bien importante es que la roca, cuando se transforma en arcillas, está blanda. Entonces solo necesitas una excavadora para trabajar, no necesitas explosivos. Entonces no usas explosivos y no tienes el proceso de destruir el sulfuro para sacar el oro. Muy interesante.
This picture, the basement is filled by alunite.
Yeah, here elinita con, well, mucho elinita, muy fino cristales. Dos.
Supergenic and alunite.
Yeah, elinita supergénica. Yeah. The hipogénica, 10 millones años. Supergénica, elinita, es 3 millones años antes. So, much younger, supergene overprint.
But this is between the water, no?
Yeah, because at 10 million years, the water table was high. Quartz, elinite, pyrite, silica vuggy, con oro. And then at 3 million years, in the Mediterranean, there was falling groundwater. And so the Mediterranean Sea lowered by almost 100 meters, and it got very small. And so in Rodicular is in Almería, sureste España. And so when the groundwater table fell 100 meters, all of the pyrite could be oxidized, supergene oxidized, which is good because then it was very easy to process for the Spaniards to recover the gold.
So in this deposit, you can find alunite supergene.
Sí, yeah, and hypogene, yeah. And the hypogene is disseminated and muy grande cristales, 5 millimeter, whereas superhénica, helenita, muy fino, cristalizado. We will look at this again when we examine this deposit type. Okay? So, okay, we will now go to, okay, now, EPITERMALES, what is the EPITERMALES? Expiration indications. After review of characteristics and processes, sometimes repeat of already discussed. Then we'll look at low sulfidation veins in zona de extensión, rifts. Then silver-rich, base metal-rich veins in arcos, intermediate sulfidation. There are many similarities between veins, but also variations. So we'll discuss some of the variations and overlaps or overprints. And this is New Zealand, Champagne Pool in Waitapu, New Zealand. Waitapu means sacred waters. This is hydrothermal eruption crater, 900 years old. We can see the eruption deposits. Now, neutral pH, liquid discharging, and this is all silica sinter. This is arsenic antimony rich colors. The black is all thermophilic algae. Thermophilic algae, bacteria, and through here. You can see starting there and then down through here. So we'll be growing up to, this is 70 meters diameter, so 70, 150 meters away, we can be growing these stromatolites here. So repeat from Lindgren, the extension-related deposits, smaller vertical interval, and commonly, and closer to paleosurface. Whereas intermediate sulfidation veins, larger, usually lower grade, and deeper. Simple observation. So, these are two end members. These are manzana y naranja. Okay? Don't worry about names. Manzana, naranja, what are the characteristics? Both have lamination de coliform. Coliform banding, coliform. This is menos sulfuros, mucho sulfuros. But these very nice coliform bands, and we'll discuss why coliform. Why is the importance of coliform? Here, abundant adularia. Basically, we get coliform because of brecciation, which leads to pressure drop, boiling, vapor loss, rapid cooling, and colloidal silica saturation. All of the coliform bands due to amorphous silica colloids. We'll come back to this later. And beautiful native gold. Here at Kochbalak in Uzbekistan. Intermediate sulfidation, low sulfidation. But intermediate sulfidation with some high sulfidation sulfides. Here, low sulfidation, but at depth, some characteristics of intermediate sulfidation. So it's complicated. complicado. So the purpose is just to show there's many overlaps in characteristics. So processes, products. First, simple observation. We use, instead of plotting concentration of gold and silver, we use economic value, roughly the present day values. We can see one group, very small value in silver, large value in gold, because of low silver-gold ratio. These are manzana, or low sulfidation. Alkalic deposits, also low silver-gold ratio. Why? I'm not sure. I'm not a specialist in low sulfidation, in alkalic. Here, much higher silver content, greater than 100 to 1 silver-gold ratio. These are naraha, or intermediate sulfidation. Arcata, no, we don't. This was made about 10 years ago, before Fruta del Norte. So Fruta del Norte should be somewhere in here. Interesting, the highest silver-gold ratios are all in Mexico. But because they're so large, they still have significant value in gold. Other lower silver-gold ratio deposits, but interestingly, they're associated with diatremes, such as Baguio, Filipina, Rocha Montana, Romania, Calian, Indonesia, Victoria in Filipinas, Cañueri in Peru. So the question is, why such variable silver-gold ratio? The manzana has low silver-gold ratio signature. The naranja has generally high silver-gold ratio, but variable. Okay. Simple answer. The manzana in sectional zones, very low salinity. And low salinity, relatively gold rich. Silver poor, and no base metals. Whereas naranja has much higher salinity, sometimes for the base metal rich, 10 to 28%. A simple observation from fluid inclusion studies in quartz veins. Okay, so observation, how to interpret. Here, this is H2S, reduced sulfur versus chloride, logarithmic scale at 250 degrees. Calculated solubilities. Low salinity, we see gold in red, silver in blue, más o menos 1-to-1 solubility. Both gold and silver transported as H2S complex. But as salinity increases, 3 to 20%, we see gold solubility in red decreasing. However, plata, silver, is also transported as a chloride complex. So silver actually increases solubility with increasing chloride. In addition, zinc is transported as a chloride complex. So higher amounts of chloride, higher solubilities of zinc. Okay? So if we have low salinity, variable gas content fluid, we have roughly 1-to-1 in solution. Therefore, precipitation will be relatively 1-to-1, silver gold. And by contrast, at high salinity, we will have very high silver versus gold in solution, and the precipitation will be high silver-gold ratio, plus or minus base metals. The geothermal systems in rifts, extensional zones, are low salinity, high H2S. Whereas in arcs, we have much higher salinity. So this is a simple explanation for the observation of variable silver-gold ratios in different tectonic environments. Not complex, relatively simple. And to illustrate then why, here we have Arcos and Rift Zona de Extensión. Deep magma chambers, 5 to 10 kilometers. Here, shallow stalks of intrusion. Here, no shallow intrusions. Maybe small rhyolite domes. They say domes. Coach-Black forms in this environment. Base metal rich veins. Kupol in Russia, manzana-like, forms in this environment. And what's the difference? In this setting of arcs, we have shallow intrusion, very high salinity, associated with intrusions, and this is redox, so oxidizing, reducing. We have relatively oxidized fluids in this environment. Anhydrite, anhydrita, baritina, sulfate minerals forming in this environment. Stable with respect to chalcoprita, tenantita, anarhita, covaline. In this environment, it's different. Pirita, pyritine, arsenopyrita, very reduced because large section of sediments, which reduces the magmatic fluid. In this environment, the sphalerita is negra, whereas in this environment, the sphalerita is miel, very light color. Why? Because oxidized Fe3+ does not replace zinc 2+. Reduced iron is Fe2+, replaces zinc 2+. So this is a simple concept. And here you can see, because of the tectonics, this is not a porphyry copper setting. Porphyry copper is in the arcs with shallow apophyses, whereas here in the rifts we have very deep intrusions that only come to the surface if we have caldera eruption. So, very clear. En español, summary. For whom is the clearest? Maybe we let JP not have Julie or Franklin or Scotland? You want to summarize? These are, of course, N members. Remember the potential for mixing or overprint.
¿Cómo explicar en español? Bueno, hay dos environamientos diferentes aquí. Como hemos dicho antes, en el arco volcánico, el magmato está más cerca de la superficie y vas a tener pequeños intrusivos que van a llegar cerca de la superficie. En el rift, el magmato está más bajo, no vas a tener estos intrusivos cerca de la superficie. Aparte que aquí puedes tener unos domos de riolita. En el caso de arriba, vas a tener fluidos con menos reducido, less reduced fluid in the arc.
Oxidized.
Oxidized
Because of the shallow intrusions. We oxidose.
So in the arc, lo que vas a tener en los arcos es que los fluidos van a estar oxidados. Van a estar oxidados. Cuando los fluidos están oxidados, la forma del eje no permite al hierro de reemplazar el zinc en la esferita. Entonces, ahí vas a tener una esferita que va a parecer naranja clara. Cuando en el rift, abajo, los fluidos van a estar reducidos. Ahí el eje puede reemplazar el zinc dentro de la esferita y la esferita va a estar negra. Entre los dos, porque la salinidad va a cambiar, no va a cambiar también el ratio de oro y de plata en los files, y entonces en la depositación. Arriba tienes más salinidad, ¿no? Sí. ¿Es eso?
Sí, exacto.
You have more salt in salinity in the arc environment.
Because of the shallow intrusion, which is separating brine to vapor. We're losing vapor, so the high salinity brine is in this environment, potentially contributing here, but not in this deep system.
Porque en el arco se recuerda que con la intrusión que está cerca de la superficie, lo que va a pasar, va a haber una separación de las fases en los files. Entonces vas a tener una fase líquido y una fase de gas. Cuando sale el gas, la salinidad de los files va a aumentar. Entonces, porque estamos cerca de la superficie, los files van a tener más salinidad. Y eso va a permitir transportar un ratio de oro-plata menor. Que en otro caso, en el rift, como el intrusivo está a gran profundidad, no tienes esta separación de gas, y los fluidos van a estar con menos salinidad y no van a llevar tanto plata. Entonces tendrán una ratio con más oro en comparación del plata. ¿Sí? ¿Es claro?
Sí.
Una pregunta con respecto a eso. Justamente lo último dice que no hay una configuración de pórfido, ¿cierto?, en la zona de arriba.
¿Que no hay qué?
Una configuración de un sistema pórfido, pero en la parte de arriba, en la zona del arco, entonces ahí sí se puede desarrollar un pórfido.
Sí, la intrusión pequeña que está arriba del baltorito, esos son los pórfidos. Entonces tienes el sistema de pórfido. Y cuando en el rift no vas a tener nunca un sistema de pórfido, porque el magmato está demasiado profundo.
Notice on this redox diagram, esfalerita menos ferro and más ferro and reduced. Again, Fe2 plus replacing zinc 2 plus. So this is esfalerita negra. This is esfalerita miel. So that's visual estimate of iron content, consistent with the two different end member environments. Oxidized shallow arc systems, reduced deeper magmatic systems in rifts.
Porque en el rift vas a estar en un ambiente reducido. El hierro va a estar en la forma F2+. El F2+ puede reemplazar el zinc 2+ en la esfalerita. Eso va a dar esfalerita que van a estar negra. Cuando en el arco volcánico, que los fluidos son óxidos, el hierro va a estar en la forma 3+. Y la forma 3+ no puede reemplazar el zinc 2+ dentro de la esfalerita. Y en este caso vas a tener esfaleritas que van a parecer naranja más clara. Es la prueba del hecho que los fluidos son oxidados en el caso de los arcos y reducido en los casos de los rift.
Now this is redox, concentration of oxygen, fugacity of oxygen. But we can go back to our concentration of sulfur. Remember, we looked at low, intermediate, high sulfidation state assemblages, arc magmas, cooling to higher sulfidation states. But we have the rock buffer here, enargite, tanatite enargite here. So cooling, when we have no rock buffer in the residual quartz lithocap, cooling can lead to enargite deposition, covalite. Remember also that in the middle of our intermediate sulfidation, pyrite, chalcopyrite, we cross from magnetite to hematite. So simple cooling causes that transition. Now, what's the importance with our rift environment? The rift magmas are lower oxidation and lower sulfidation state. So those fluids just follow the rock buffer through 5 or 10 kilometers and they end up basically still in the low sulfidation environment. Pyrite, pyrrhotite, high iron sphalerite, arsenic pyrite. So these sulfides are actually reflecting the tectonic environment. They're reflecting the magma chemistry. Again, this is a simple examination of what is case by case more complicated, but still we can simplify it, I think, from this perspective. That epithermal mineralogy is reflecting the tectonics and magma composition. Fundamentally, this is coming from a magmatist. If you're not, you won't believe this. So I don't want to go into the detail, but there is an argument for why these different tectonic environments have different characteristics of mineralogy. Okay? Yeah.
Las iniciales PO, ¿a qué se refiere?
PO es pirrotita.
Pirrotita. FES.
LO?
Oh, lowlingite.
Loki?
Lowlingite. Lowlingite is FeAS S2, similar to arsenic pyrite, but lower sulfidation state, very low. Lowlingite, it's Lowlingite, Lowlingite, the Swedish mineral, Lowlingite.
MT is marmatite.
No, MT is magnetita. Magnetita, hematita. Bornita, magnetita. Remember, in our high temperature porphyry roots versus chalcopyrita in the cool part of porphyry, in the lithocap, cooling into enargite stability. And usually, we do not see these minerals in low sulfidation environment. They're close to the iron-controlled wall-walk buffer. How would you define buffer in Espanol, Richard? There's some argument here. Do you know, or I guess some people decided that buffer is
unlimited.
No, es algo que da que limita un poco un efecto, como que tampona algo, por ejemplo, que sin lo que se llama el buffer o algo buffer, sin eso los fluidos cuando se enfrían haces una línea recta que va en la zona de alta sulfuración. Pero ¿por qué hay hierro dentro de la roca? Eso no hace que el fenómeno está un poco
no permite
limitado. Sí, que no se permite. Entonces, porque el F va a comer azufre. No vas el rango de azufre va a bajar y eso va a hacer que tú vas a quedarte en la zona de intermediate sulfidation.
Porque hay un montón de hierro ahí. Entonces el azufre el fluido está empezando a enfriarse y quiere que enfriarse y está enfriando, pero hay siempre un montón de hierro disponible para chupar el azufre. Entonces quiere que ir a la autosulfidación, pero no puede porque el hierro siempre está sacando y chupando el azufre, entonces no se puede desarrollar un contenido de azufre alto.
Y como este hierro viene de la roca encajante,
Que hay
dice
un
que
montón de hierro ahí.
se dice que la roca encajante disminúa el efecto de la bajada de temperatura, porque tenemos el azufre por un lado y la temperatura por el otro lado. Entonces, esa es una curva así que se crea. En el caso del rift, los fluidos son si no me equivoco, reducidos. En este caso, va a seguir la línea que da el efecto de la roca encajante con su contenido en hierro. Y nos vamos a quedar en baja sulfidación.
Jeff, sorry, pardon? Did you go through those curves as to the porphyry copper?
Yeah, that was this morning's porphyry copper discussion. We've been through this.
Okay, and then going down into the intermediate and high sulfidation.
Yeah, and off there. That was 5-10 minutes discussion already. So this is just a repeat of a portion of the one. So let's look at this tectonic environment. Zona extension and magnetism in a rift. Remember I said topovolcanic zone is a back arc rift. Here we're looking at rhyolite dome, Domo de Rhyolita, about 700 years old. And in 1886, it was split by a basaltic fissure eruption. Classic bimodal rhyolite basalt tectonic setting. At the same time, there were phreatomagmatic eruptions that formed this lake and destroyed this geothermal system, silica sinters. And a few years later, phreatomagmatic eruptions, the so-called Waimungu geyser, but the Waimungu geyser was throwing 1 meter blocks, 400 meters in the air, ballistic. That was not geyser. And you can see, Waimungu is black water. So these are muds. So hydrothermal or phreatomagmatic eruption. These must be some geophysicists running to look at the eruption. And notice here, these are turistas. Even 120 years ago in New Zealand, tourists liked to get very close. And in a later eruption, there was a lateral blast and it killed 3 tourists, or 1 guide and 2 young female tourists. So that was happening here. Just south of these dacite domes is Waitapu with Champagne Pool and another hydrothermal eruption crater here. So let's take a look now at Waitapu. Waitapu means sacred waters. Here are the dacite domes, fractures, and these are fumaroles. Fumaroles and steam heated activity, which we just reviewed in the last lecture. Here is an example. This is CO2. pH 2.5, kaolinite muds, but the bubbling, that's not boiling, that's CO2 lost. And similarly, we see smaller bubbles coming out, CO2. Kelonite muds, pH 2.5, the CO2 bubbling through in these areas. These are all hydrothermal eruption craters about 900 years ago. So we'll look at them. This is actually filled by a lake, but we can see these are all hydrothermal eruption deposits. I mapped this area for my PhD, and fragments of altered clast from 300 meters depth. We have geothermal drill holes in this area, so we know the stratigraphy, and so that we know how deep the fragments came. Here, fragments from 170 meters depth. Okay. Names. Champagne Pool with silica sinter, now Cold Lake filling it, and Lake Fungiotrangi, a cool acid. Now we'll look at Oblique. This is looking north to south. There is Lake Nokoro, that cold water lake, but with some acid inflow. Lake Fungiotrangi, an elongate hydrothermal eruption crater filled by cold acid waters. And there's a fault in through here, hanging wall on this side. And notice that the steam-heated acid sulfate features are in the hanging wall of the fault. Okay? Why steam-heated features in the hanging wall of the fault? Pardon? Gas is what?
Gas and heat.
You had it clear? But vertical, yeah. Yeah. Vapors don't go into the foot wall over here. No. Very simple. The vapor, liquid boils to the hot spring vent. The vapors rise vertically. They're buoyant, and they travel through lower permeability. Vapor is low viscosity, so it can travel through lower permeability rocks in the hanging wall, but also long fractures. Okay? So these are eruption deposits here, actually over here too. This is area of steam-heated alteration and collapse. And right there is silica sinter. This is what the silica sinter looks like. Laminations, vertical growth structures. And through here. Oh, and then subsurface, the acid sulfate waters flow out, and then right at this point, pH 2.2 waters flow to this stream valley. And here we see the stream valley. This is laminated silicious rock. Some people have called this sinter, but when we look closely, we see accretion lapilli. This is airfall tuff. And so this was the aquifer for outflow of the silicifying waters at the base of the groundwater table. Why is it exposed now? Because this stream has eroded about 1 meter, and now the opal silicification is exposed. But this upper surface is very flat. It runs into this area here, and you can follow it as you walk up the trail. This was the paleo groundwater table. Now the groundwater table is at the stream. And that's where the hot waters discharge. scale 100 meters. So we can see hot pool, silica sinter, various eruption craters, seamid alteration, chalcedony, the base of seamid alteration. That can give you the sense of scale for just one system. Really, this is this is 500 meters here. If you happen to focus on this area, you're going to be distal to, even though this is silicified, if you focus here, you're drilling, you may not hit the vent area proximal to the hot spring. So keep in mind the potential scale, just like we showed at Yellowstone yesterday. Okay? Let's go to this lake right here. This is pH 2.4, cool acid sulfate waters. This blue-green color is because of silica colloids in suspension. And part of this crater lake is now drained, and we can see the deposits. Finely laminated. Is it silica sinter? No. We see that this is actually cross-bedding. So cross-bedding means sublacustral. Here, acid crater lake, acid sulfate crater lake. And these fine laminations would just be continuous. We don't see any vertical growth structures due to evaporation or thermophilic algal stromatolites. So the lack of evidence is not evidence, but sometimes if we don't see anything indicating silica sinter, maybe it's not. These are alternatives for finely laminated siliceous deposits at paleosurface. Similar to the laminated deposits at Yanacocha from a deposit from acid crater lake. But you can imagine if this is recrystallized and we look at this, if we look at that, we might, or just here, we might say, finely laminated sinter. But I say, be careful with the use of sinter, because this lake is over here, 300, 400 meters from true sinter and discharge of the neutral pH vent. That's sinter there. Okay? So even if you cannot interpret the texture, at least describe the texture. Fine laminations, no replacement, local cross-bedding, etc. No vertical growth structures. Versus other massive silicic with growth structures, etc.
This case is not like a
Pardon?
It's not like a
Well, if you only see this, this is not lithocap, but it's similar to the bedded colloidal silica at Yanacocha. But if we look in this area, no silica vuggi. No, we see shallow layers, kaolinite, steam heated, but very quickly, 10 meters deep, we get smectita, illite smectita, indicating neutral pH. But if you only have one outcrop, subcrop, right here, you know, you're not sure, but at least you could say maybe this is paleosurface of some system. Don't know the type.
It's possible to know how long is the silica is, or how far is from the center of the
There's no quantified geochemical anomaly and whatnot, but I'll show in near the end of, before tea break, probably, I will show you how large the silicification can be at paleogrometer table. It can be at least 2 kilometers. How to say what's proximal, what's distal? Well, we'll discuss it more. Okay. This is some finely laminated material from Tambillos in the central Peru, about 4,000 meters. This is finely laminated, no plastic, no replacement textures. I interpret that this was basically analogous to fine colloidal silica precipitated in a shallow lake, shallow acid lake. Silica sinter is amorphous silica. So the deep, high temperature fluid in equilibrium with quartz, it has to cool rapidly to reach, at boiling temperatures, to reach amorphous silica saturation, to form amorphous silica. If it was, say, down here at 100 degrees, it would not precipitate amorphous silica. Why this slope? Because as we boil, we cool, but losing vapor also concentrates the silica in the liquid. So we're concentrating the silica a little bit. So neutral pH boiling liquid reaches that. Amorphous silica. Champagne pool sinter, silica stromatolites. That's 5 millimeters. So 1 centimeter there. These are each about ½ centimeter or 1 centimeter in size. Very similar to size of Fruta del Norte. Stromatolites. Oh, here. Silica stromatolites, Fruta del Norte. 1 centimeter. Roughly the same scale. And now here we see very nicely developed stromatolitic texture. As I said yesterday, the only unequivocal diagnostic feature of silica sinter because of the thermophilic algae. Okay? Yeah? It's very rare. I mean, Fruta del Norte is a very special deposit in many ways, including some of the textures, but including this texture here. And this really discovery of the sinter is what told them, even though no gold, we back up and drill underneath. And that was the discovery hole. Okay. Well, what happens if we boil a deep liquid, removing vapor, cooling by removing vapor, and also increasing the silica concentration? We can reach amorphous silica saturation and form colloidal silica gels at higher temperatures below the surface. Why is that important? That explains colliform bands. Colliform banded quartz veins is consistent with boiling and deposition of colloidal silica. The microscopic textures show that this is not deposited as quartz, it deposits as silica gel layers. And silica gels, colloidal silica gels, are amorphous. We must reach amorphous silica saturation. So, colliform bands anywhere. We saw one sample yesterday. That is a positive indicator of boiling. Doesn't prove that you're going to have a gold deposit, but at least it tells you about one of the processes. And the more you find, almost all bonanza gold, epidermal gold veins have colliform bands. Majority, 90%, I would say. And that's how it forms. Somewhat similar to the formation of silica sinter. This, you could say, is subsurface equivalent.
In this colorful wavelengths, what happened with the pyrite? Sometimes the same shape.
Yeah, pyrite can also locally be coliform. Very rapid, the coliform bands indicate supersaturation. Very extreme supersaturation. Coliform pyrite is also, or marcasite, also suggests supersaturation. Very rapid cooling. So I don't know, but I'm guessing that it's a similar process. So, and how does it form? Because we brecciate and allow rapid pressure drop, decrease, which leads to boiling, vapor loss and cooling, amorphous silica gel formation, and if gold is in the liquid, vapor loss also causes gold deposition. If no gold in the liquid, you can boil and cause these textures and have no mineralization. But when there's gold in the liquid, this is a very positive indicator of the process that leads to gold deposition. So if you get outcrop, subcrop of these textures, definitely identify and plot the areas. Okay. Some people, one person particularly, I won't tell you which country in the world they come from, but they speak with an Australian accent, argue that all of this, clay alteration, coliform banding, it's all caused by mixing. Impossible. We take any liquid on the quartz solubility curve and mix it with cool waters. Nowhere will we reach amorphous silica saturation. We cannot form silica sinters. We definitely cannot reach colloidal silica gel formation. It's just that he gives a short course, and if you took his short course, you would believe that, this disagrees with him. I've had people who said, but what about mixing? And I know they took that short course. And I have to explain, well, this person is not a geothermal specialist. They don't really understand the fundamentals. So boiling is the most critical process. Mixing does occur. Shallow depths, margins, yes, it occurs, but no es importante por oro plata, yacimiento de oro plata. Boiling is the principal important process. Okay? We'll come back to this again when we talk about laminated gels in high sulfidation process, the same process. So back to topovolcanic zone, our volcanic arc to the east. White Island is north about 30-40 kilometers. Here is the rift margin and rhyolite dome right on the margin with basaltic dikes. Waiatapu here, and this is Broadlands, Oaxaca. This is the Oaxaca pool boiling hot spring formed with silica sinter apron. And these are discharging wells. Very strong discharge, and each well is $2 million. So we study the geology, the alteration, the fluid composition very carefully. So we have large amount of information from these types of systems. from geothermal drilling. So let's look at alteration. Stuart Simmons took information from the wells. For example, at 400 meters depth, plan at 400 meters erosion. The measured temperatures are plotted here. High temperatures in the middle, lower temperatures on the margin. Each of these data points, that's one well. The pink is where the temperature is greater than boiling point at 400 meters depth. So this is boiling, this is subboiling. Then he looked at the mineralogy. This is illite. Outside is illite smectite or smectite. So empirically, in español, empirically, empíricamente, illite is alto temperatura, smectita is bajo temperatura. That's the distribution we see. Also, this area here has strong adularia. Well, if this was a prospect of 2 by 4 kilometers, in 1 or 2 days, you could collect these samples, examine in the field camp the shortwave infrared characteristics, identify the different clays, and say, this is high temperature area, all of this area, but this area also has adularia. I can see it with my hand lens. So let's focus on this area. And right there, in a few days field work, you've focused to 10% of the area. But why is adularia important? We'll come back to adularia in a few slides. But let's look at clay mineralogy. These are most of the minerals in the epithermal environment, plus sulfurous. In low sulfidation settings, rifts, illite clays, adularia, calcite, very common. At neutral pH, we can see smectita, illite interstratified, illite smectite, chloride smectite, or illite, simple temperature increase. This information comes from geothermal studies. So these are mineral geothermometers. They indicate the temperature. Adularia, basically, it probably is not stable below 150, but adularia has wide range of stability. Same with calcite. But most importantly are just the clays. We'll look at several examples as we go. Remember, from Lindgren, low sulfidation deposits, shallow formed, less than 200, 300 meters depth, low temperature. Less than 200, 220 degrees. So clays are important. Illite, interstratified clays, smectite. Intermediate and high sulfidation deposits form deeper, 300 to 800 meters depth. Temperatures are higher, and so we have a different assemblage of alteration minerals. Of course, there's overlap. Okay? We'll come back to this several times. This is just the framework for interpreting the data, the mineralogy. So that is the important environment for low sulfidation. Looking at zonation, indicating higher temperatures.
Excuse me, there is a seat in the reef. In
Calcite?
yeah, in the earth. In the
Both,
consolidation
yeah.
earth.
Carbonates, maybe less calcite, more carbonates, such as manganese carbonates, either manganese calcite or rhodochrosita.
Yeah, but no calcite.
Oh, there's calcite, but other carbonates are also important. But in low sulfidation rifts, solamente calcita. Yeah, very rare manganese carbonates.
So sorry, Jeff, can you just go back to that last slide? Okay, so calcite you only see in alkaline.
Not only, well, first of all, calcite is not stable in acidic,
Yeah.
but let's forget the alkaline. That's just slightly alkaline.
Okay.
It's basically boiled liquid, and we'll show why adularia and calcite form in slightly alkaline, i.e. boiled liquids, in a few slides.
Please, in the alkaline fluids, zeolite minerals is alkaline. It's possible to predict how deep is the fluids with long.
Well, these zeolites,
These are, yeah.
mordenite, lomentite, wyrokite, also have very clear temperature, reflect temperature patterns. But
So all three of those are zeolites.
calcium silicate, zeolites, yes. But they only form in low CO2 systems. If the CO2 is high, the calcium forms calcite with high CO2, and we do not see zeolites. And in fact, we want to see gas-rich systems. High CO2 means high H2S. And high H2S, as I'm going to show, means high gold solubility as a bisulfide complex. So usually in epithermal ore deposits, there is no zeolites, no significant zeolites.
Glauconite is zeolite.
Yeah, but not that common. They're sometimes present, but we do not get massive zeolites unless the system. Wyrokite. Where's wyrokite from? The geothermal system at Wairaki. Wairaki is a low gas system. Nearby Broadlands has 50 times as much CO2. There's no wyrokite. There's no zeolites. But there are carbonates reflecting the higher CO2 content. So if I saw two systems with carbonates here and this one with lots of zeolites, I'd say I'd like the gas-rich, CO2-rich system, because that tells me there's also high H2S. Because the CO2 H2S ratio is relatively constant, 10 or 20 to 1. It's empirical, whether it's low gas or high gas. Why low gas versus high gas? Magmatic contribution. CO2 and H2S simply reflecting, coming from the magma. So I prefer high gas systems, and as we'll see, H2S is important for gold transport. Okay. Let's get back here. I showed this diagram earlier. Remember 400 meters depth, that map? So we have illite and adularia. To the south, it's smectite clays, illite smectite clays. These are measured temperatures, and the reason for the adularia here, that's a zone of boiling. And I'll show fairly soon why boiling causes adularia instability. But the clay pattern here reflects the measured temperatures. Lower temperatures in this area, more clays. Here, very shallow, very low, high temperatures to shallow depths, and we get very narrow smectite horizon. So boiling in this area, rising along fracture, discharge from Ohaki Pool. Some of the vapors rise to the Vedos zone, zona de Vedos. The H2S oxidizes to sulfate, and pH 2 to 3, we get boiling mud pools of kilnate. But also, if the vapors condense below the Vedos zone, as I showed earlier, then we can have CO2-rich fluids. Remember, these geothermal wells discharge very rapidly, high temperature production wells. This well on the margin, this is just bubbling, indicating CO2-rich conditions. In fact, it was precipitating aragonite, silica supersaturated, supersaturated calcium carbonate. So that is our CO2-rich carapace. As we said, beer has pH of 4 to 4.5. Why? Because of the CO2 carbonic acid. Here, this is also pH 4 to 5. I know, I did the study here because we lost a stainless steel casing at 400, 500 meters depth here, and I was given the job to find out why. And we found out that, in fact, this area was carbonic acid, which was attacking, dissolving the stainless steel casing from the outside in. And along with this, we get kelnite. Not kelnite from steam heated alteration, but deep kelnite with smectite, illite smectite, and carbonates, including some carbonates, iron carbonates. You were asking about carbonates. There are some iron carbonates here as well. So this is important because this helps us interpret why we have deep kelnite, for example, in the hanging wall of Kupol. Kupol is an 8 million ounce low sulfidation deposit in Russia with illite kelnite at 200-300 meters depth. Not steam heated kelnite, but CO2 condensate related.
Jeff, sorry, just go through that kelnite formation again, please.
Kelnite is stable at about pH of 4.
Yeah.
Because here we see this well right here discharging from this zone. It is dominated by CO2-rich fluid due to the condensation of CO2 on the margin of the system. Just like your beer, carbonic acid produces a pH of 4 to 5. I measured this pH by collecting the deep fluids. We had a downhole sampler designed especially for this to capture the CO2, the pH 4 to 5. Well, pH 4 will cause kelnite to form. We don't need acid sulfate waters down at this depth, which is how some people interpreted it. We can actually have kelnite present in equilibrium with clays.
So in this zone, maybe there is a subpyrite.
Oh, yeah, sorry, I should have put also pyrite, mucho pirita. Yeah. So again, schematic, but we'll then, with this framework, we will interpret observed clay zonation around veins. Okay, the production wells measured temperatures follow boiling point for depth. As the liquid rises, the pressure decreases, it boils, cools, and rises further. Then boils more, vapor loss, cools, all the way to the surface. So in this area, we have 200 degree temperatures at 150 meters depth. So that's basically illite and adularia occurred at 150 meters depth, the narrow zones of illite, smectite, and smectite. By contrast, on the margins, we have mixing going on. And we can have very deep zones of 200 degrees, 500 meters or more. And for that reason, this is not boiling. For that reason, we can be very deep before we get illite on the margins. We have thick sequences of illite, smectite, and smectite alteration, including kaolite. So, for exploration, if we see thick sequences of these clays, we're distal. But if we see very narrow zones, rapidly increasing zones, smectite, illite, it indicates higher temperatures, high gradient of temperatures. We want to be closer to the upflow. We do not want to be drilling the margin or outflow.
That's counterintuitive.
What?
No, you think that you're looking for the biggest alteration zone.
Not if it's low temperature, not if it's due to mixing on the margins. We've got big zones here, distal. You want to be where the paleoisotherms are the closest, indicated by the mineralogy, which is the replacement, the measurement of paleoisotherms. You want to be here, very close together isotherms. You don't want to be out here. This is the margin zone of mixing. You want to be right here in the zone of rapid cooling due to boiling, because rapidly cooling, boiling fluids indicate upflow, and also the process will precipitate gold.
Jeff, can I just make sure that we get that?
Okay. The cross section, or
well, let's just start with the cross section.
I want to know the temperature in this part where you are having kaolite.
measured temperature. That is 150 degrees.
Yeah.
And 500 meters depth.
Okay, yeah. I saw this alteration, the silica is chalcedonic silica plus
Chalcedony indicates low temperatures.
Exactly.
Yeah.
So the plate is this alteration.
That would be consistent with the marginal illite kaolite alteration, chalcedony, low temperatures on the margin of the system. That's why when you mentioned that earlier, I was thinking, but I didn't want to say anything until I showed you this. Richard?
Señores, esta cosita es fundamental, porque hace una semana mi jefe estaba pegándome porque estuve diciendo que en Japón están perforando debajo de un sinter. Y mira, perforaron 400 metros de arcilla y ustedes están perforando roca verde. Que no tiene nada, tienen que buscar la arcilla. Y Y estos dos diagramas son fundamentales porque ya se está diciendo que obviamente estas son los controles de temperatura. Entonces aquí, esta es la zona de flujo. Entonces aquí está concentrado el agua o el fluido está más caliente, mientras aquí la bajada de temperatura es mucho más gradual. Y hay un montón de arcilla desarrollado en esta zona debido a la mezcla de los fluidos. Y en la próxima diagrama, mira, está diciendo que un fluido, lo que se necesita es que el fluido sube y reacciona lo más pronto y lo más rápido posible. Entonces, una línea que está así, entonces esta es temperatura en este sentido y profundidad. Entonces se necesita una curva que es casi vertical. Y lo más vertical, que es lo más rápido todo el proceso. Entonces vas a tener un cambio de estas minerales, de alteración, pero muy seguido, muy rápido. Entonces, una vez de cuarzo en este ambiente de epitermal, si vas rápidamente de hilita, una salvada de hilita, y de repente hilita, espectrita y un poco de calderita tal vez, en una manera rápida, estás en una zona más interesante, porque está diciendo que el fluido está subiendo rápidamente, está reaccionando rápidamente. El rato cuando estás en un ambiente aquí, donde este es el fluido de interés, este es el fluido de la roca encajante. Entonces, cuando estás mezclando los dos fluidos, vas a tener una reacción, la zona de arcilla sería mucho más extensiva que esta cosa. Entonces, si empezamos a perforar un montón de arcilla, puede ser una zona interesante, pero estás afuera. Estás en esta situación.
En el margen de la...
Entonces, lo más rápido que es el cambio en las salvadas de la beta, lo más cercana estás al centro de la... Y yo siempre tenía ese concepto de inverso, cuando hay una beta con cambios bruscos, pensando, el sistema está inventando, pero en realidad es el inverso.
Yeah, we want high temperature gradient indicated for mineralogy. So, I've been promising this for a while. Adularia, right? Rhombic shapes. We saw beautiful rhombic shapes from Yowie and Crunchy? JP? Adularia, Yowie
y
Sunny. So, why is adularia important? First, if we lose CO2, well, first of all, CO2 in solution is carbonic acid, cerveza. pH 4.5. If we lose CO2, this reaction goes to the right. Consumes hydrogen, pH increase. And of course, if we have a bottle of beer, we leave it open overnight, next day we drink it, not so tasty. Why? No CO2. It doesn't have the sparkle and loses the acidity. So loss of CO2 causes pH increase. Okay. If we have illite, like at Broadlands, wide area of illite, and we write equilibria with adularia, we have to balance it with hydrogen. If we lose the hydrogen by boiling due to CO2 loss, the hydrogen decrease will cause this reaction to go to the right, from illite to adularia. So adularia is empirical, it's consistent with empirical evidence for boiling, particularly when you have adularia in veins and illite in wall rock. Very simple. And we see this in most veins. Adularia is focused in the veins, sometimes in the hanging wall, but proximal to veins, because maybe the boiling extends into the wall rock as well. I'll show you some examples from Waihi in several slides. So this is impure. This is positive, at least again for boiling. It doesn't mean gold, but it indicates the process that could also precipitate gold. Why do we have bladed calcite? Or more often we see quartz pseudomorphed after bladed calcite. Same thing here, CO2 loss. This is the reaction controlling calcite solubility in geothermal systems. We lose CO2, this reaction goes to the right, precipitates calcite. If very rapid loss of CO2, supersaturated, and supersaturated calcite forms blades. This sample is from a geothermal well that was boiling. So, here Hishikari, bladed carbonates, indicating boiling. Again, does not prove boiling, but it's consistent with boiling. I think this almost certainly indicates boiling, but not always where gold is precipitated, but still indicates the process. And finally, why are we interested in boiling? Effervescence, or en español? Boiling? Evolutionation, yes. This is from Sleeper. This 3 millimeter band here, native gold. Here we see one of these gold dendrites here. This gold dendrite with like a snow bank of coliform silica, colloidal silica over the top. Here's coliform quartz, gold precipitation, and then calcite, bladed calcite, but pseudomorphed by quartz. And the reaction, again, is very simple. H2S in the liquid. Boiling, just like CO2, H2S is volatile. It is lost to the vapor phase, and so boiling causes H2S loss, and this reaction goes to the right, precipitating gold. Very simple reactions. You can precipitate gold by mixing. If you cool 50 degrees, you decrease gold solubility by half. If you boil 10 degrees, you cause, over 10 meters, you cause gold solubility to decrease by 90%, 1 order of magnitude. So yes, mixing will precipitate some gold, but boiling is order of magnitude more favorable. And boiling occurs where you have the upflow. Mixing is out on the margins. So these are simple reactions that explain why some of those clays and adularia calcite are important. as well as even, remember, how do we get colloform colloidal silicon? Boiling and vapor loss. It's all consistent. Sorry, JP.
So maybe a crazy question. So
Only crazy answers, no crazy questions.
maybe so the boiling could occur over a large area, like in the same system, you can have the boiling during 100 meters or more than 100 meters. Or
1 kilometer.
1 kilometer.
This is all boiling here.
Okay.
All of this is boiling, but in addition to boiling, we also want to focus our boiling liquid along structures.
Okay. You will have the discharge of the precipitation of the gold at the beginning of the boiling. No, because as soon as the fluid starts boiling, you will have a decrease of the solubility of the gold, so you will precipitate. No.
When you boil, you'll also lose hydrogen. And on the initial, hydrogen fractionates to the vapor even faster. So on the start of boiling, this reaction goes to the left. First boiling actually increases gold solubility. Those are details that I don't want to get into. I can give you the paper by Stuart Simmons, but first boiling very rapidly causes calcite deposition, calcite saturation. But first boiling also causes gold solubility increase. So that's why even if we see a lot of ablated carbonate, it may be associated with the base of boiling, but gold is at a more shallow depth. That's one factor. The other factor is in very rapidly ascending fluids, even though we saturate with respect to gold, gold may not precipitate. Gold may form colloids. In 1908, Lindgren recognized gold dendrites in Nevada, and he said that's due to gold colloid deposition. Everybody said, no, you've been smoking too much. No. In 1990, Jim Saunders proved here that these gold dendrites are due to gold colloid deposition. Anybody retire and get a gold-plated pen? If you want to plate this with gold, what you do, you put it into a suspension of gold colloid with a charge here, very small charge, and you plate the gold. But if there's too much gold colloid in suspension, suddenly the plating stops and you grow dendrites. So independently, we know from metallurgy that high colloid concentrations create dendrites. And I can send you those papers as well from Jim, which demonstrated that these gold dendrites, which are present in many bonanza gold deposits, are due to gold colloid deposition. Now, in low sulfidation deposits, why do we have smaller vertical interval at a shallow depth? Only boiling at shallow depth? Maybe it's because the deep liquid is ascending so fast with gold colloid in suspension that it comes up to a shallower level. And we get the typical horizons of bonanza gold. Whereas in intermediate sulfidation systems, in arcs, we have the same amount of gold, but at lower grades over larger vertical intervals. It's only a speculation, but I think there's something to it because we see so much evidence for gold colloid deposition. So now it's not simply a chemical precipitation, it's also a physical deposition. And most low sulfidation bonanza deposits have a very sharp top, like Kishikari, I'll show, very sharp top to high grade. 100 grams per ton, and 10 meters higher, less than 1 gram. That's almost like a physical limit, physical upper limit to the colloids. So a long answer to your question, but there are several reasons why first boiling doesn't cause gold deposition. And even if it does cause gold supersaturation, we may get gold at shallow levels. So ask me that same question afterwards, and I'll give you all these papers to support. Those are the details that usually I don't go into.
No, but so it was not a crazy question.
No, it's not a crazy question. I think the reality, it all comes together, and most of it is, much of it is confidence from studying active geothermal systems where we can get burned by looking at the actual hot waters. And we see these things directly. We don't have to interpret.
Another maybe crazy question. If you had a lot of another gas into the fluid, like CH4,
Methane, yeah.
If there is a lot of carbon in the area of the system, what will happen?
Both McLaughlin and Esquel have high-grade, low-sulfidation deposits. At first, some people said that's why McLaughlin is a special deposit. Gold precipitated due to the petroleum from the Great Basin sediments. But careful study shows that petroleum is just part of the system because the hot water system in the basin, it matured the petroleum. But the gold is largely precipitated separate from the carbon. Same in Carlin. At first, the idea that carbon caused gold precipitation. No, all the gold is in Arsenian pyrite at Carlin. So there appears to be no clear relationship for any significant effect of carbon, of reducing carbon on gold precipitation.
Jeff, sorry, just go through those reactions again. So the CO2 boiling in a top reaction, that is a physical process. That carbon dioxide is boiling just because it reaches.
It rises to its boiling point at the vapor pressure.
Right. Okay, so that's physically driven. That's CO2 coming off. Okay, and so that causes the pH to decrease because you've got hydrogen increase.
CO2 is the primary CO2 buffer, pH buffer in these low salinity systems. Carbonic acid, we lose CO2, carbonic acid consumed, pH goes up. Hydrogen ion decreases. Hydrogen ion decreases, but of course, pH is minus log the activity of the hydrogen ion.
Yeah.
So high hydrogen means low pH. That's the reaction. So, these are actually we can come back to later. But let's just, look at one or two examples, and then we'll break for tea, and come back for a second lecture, and then we'll break for cerveza. And we will test the gold solubility. In cerveza, one person is going to shake up their beer, and we'll measure the gold solubility. McLaughlin, the origin of the term hot spring gold deposit, which is misnomer, incorrect. In Espanol, misnomer, misnomer is incorrect use of a term, of a word. Okay, I'll show you. Here, laminated with vertical growth structures. This is the center at McLaughlin. 100-ton gold production of gold. 1 million year bimodal volcanism. And this was first mined for mercury 100 years ago. Nobody analyzed for gold. Homestake had the clever idea, let's look at all mercury prospects and mines in California, 300. 2 of them had detectable gold. This deposit, epithermal system, and a nearby epithermal system, smaller, 10 tons of gold. Everything else was related to tectonics, not epithermal. They drilled a hole underneath the center, found sheeted veins, colliform bands, local oil. These dark bands are petroleum from the Great Basin sediments, but not important for focusing the gold. And so the term hot spring gold deposit was coined. This was one missing link, although Lindgren and others had suggested epithermal veins being and sinters having similar textures. Nowhere did they see that direct link. Whereas here, directly below the sinter, is the sheeted vein complex. So, hot spring gold deposit, special type of gold deposit, new type of gold deposit. Let's look only for silica sinters now. Well, how many sinters did people find that were not sinters? I expect most. They found any siliceous laminated material. They collected samples, no gold, or walk away. Except that most sinters do not have gold. Most true silica sinters do not have gold. Here, also, the report was gold in the sinter. In fact, gold is in the fractures cross-cutting the sinter, but not in the sinter itself. Okay, so we have Coast Range ovulites, Knoxville Formation thrust over the ovulites. This high angle thrust fault was permeable horizon. As the liquid discharge precipitated silica sinter, but then that discharge point was sealed by mineral deposition, pressure built up, and then there was a hydrothermal eruption. And the hydrothermal eruption blew out fragments of silica sinter and incorporated it in a muddy breccia. And then new permeable channel way, more silica sinter, followed by mineral sealing, pressure build up, hydrothermal eruption, etc. Multiple pulses. And so there are veins cutting through the sinter, and those veins contain gold. This is the sheeted vein complex here. Here is the brecciated sinter. So, my question is, this is 1 million years old. What happens 1 more million years and we erode this system 20 meters depth? No sinter. Should we change the name? Now, due to erosion, we must change the name. No. This is simply a classic epithermal vein with evidence for paleosurface preservation in the sinter. It's simple. It's not a special vein system, different vein system. It is only with paleosurface preservation. And even steam-heated kelnite alteration in the hanging wall, which is the yellow. So it's, this is the link, really, to the geothermal systems. And then we had increased confidence that our geothermal studies really were applicable to epithermal. Okay? Yeah, I mean, You can go to the original papers, get more details, but this is just the concept, showing you the sinter. Now, obviously, this was low relief. Veins coming right to the sinter. But if you have higher relief system, upflows may actually go down the hydraulic gradient, and the sinter may be offset from the upflow. So be careful about, even if you find true sinter, be careful about just drilling right there. Think about the paleohydrology. Was it low relief or high relief? Low hydraulic gradient, high hydraulic gradient. I'll show you another example in these arc systems where silica sinter is 3-4 kilometers offset from an active geothermal system upflow. Okay, I realize I went through this rather quickly. You can come back. This is the example to address Franklin's question, I think. Ivanhoe, Nevada, a Hollister gold system. This is the Hollister pit, mined in the early 1980s, disseminated gold, 1 gram or less gold, hosted within, well, here's overburden, but basically hosted within the felsic tuffs here. Notice here porphyritic flows, and subsequently the feeder veins, high-grade feeder veins in the basement were discovered here, but blind, below the felsic tuffs. But this is a nice illustration of the, what they call chalcedonic silica cap. These are groundwater table zones of silicification for up to, what? 2.5 kilometers north of these source veins. And notice that these deposits don't extend to the south. They are asymmetric. Again, we discussed earlier, maybe not everyone, due to asymmetric hydraulic gradient. The hydraulic gradient must have been to the north. So if you see this chalcedonic silicification, don't drill right here. You may be as far as 2 kilometers. First, map out the whole area, and then look for evidence for what was the direction of hydraulic gradient. Because basically, we probably want to look at margins of this silicified cap, the silicified horizons. This is a silicified, we can see opal, and also, what is the texture of this rock? Is it silica deposition or silicification? Silicification. What does that texture look like? Well, conchoidal fractures, so low temperature opaline, but the primary lithology is crystal tooth. 3/4 of these opaline silicified horizons are after airfall tubes because they act as aquifers. They're the natural shallow aquifer for outflow. So extensive outflow along this felsic tuff. Right over the veins, we actually have kelnite mixed with irregular opal. This was actually up in the Vados zone, and the silicified waters draining down to the groundwater table, then flowing off to the north. So, north-south section here. Originally, Robert Fielding's company, Ivanhoe, in the early 80s, they were only interested in bulk tonnage, heap leachable gold mineralization. So what do? They're only drilling vertical RC holes looking for gold. And this might have been 0.2 or 0.4 grams through here. And they knew there were no veins in the basement, so as soon as you hit the basement, of course, you stop drilling. This is called dogma. Because in fact, they hit some high grades in the basement, such as here, 5 meters, 6 meters at 30 grams per ton in the basement there. Let's see, what else? I guess I don't have any others here. But Hunter Dickinson, where's the, I don't have a label. Hunter Dickinson looked at this data 20 years later, and they recognized high grades in the basement. Oh, must be due to high-grade feeders. So they acquired the property, drilled angled holes, and of course, they intersected the high-grade feeders with, you know, 2 to, half to 2 grams of ounces per ton gold in these feeder zones. Yeah, 15 to 50 grams per ton. So yes, there are veins in the basement. And that's what fed this plume. But interestingly, the plume, gold plume, must have migrated to the south because we don't have much drilling here, but this reconstruction suggests the gold to the south. And we know the mine pit, Hollister Pit, is to the south, 300 meters. So outflow, alteration of these tuffs, and notice where the chalcedony is. Oops. High grades. Notice where the chalcedony horizon is. And this upper tuff stops here and then extends to the north, as we could see, 2 kilometers. So shallow groundwater hydraulic gradient to the north, deeper a hydraulic flow of the hydrothermal fluid to the south. So a beautiful example of the development of these extensive chalcedony horizons and outflow. Keep in mind, important just to map out all of the features and record the elevation. Maybe you find changing elevation, but possibly that's simply due to post-mineral tilting or 2 horizons, possibly post-mineral faulting. Or maybe there are 2 horizons too. Okay, we are going to, I think, take a break and come back and look at Hishikari, the world's highest grade gold deposit, not just epidermal, gold, 50 grams per ton. This is a 440 ton gold production plus reserve deposit. And they have not drilled out the deposit yet after 30 years. They mine it at what? 6-7 tons a year. Just because they don't really need it. This is Sumitomo. This is not a gold mine. This is a silica flux quarry underground. Because all of the quartz goes to their copper smelter. They use the quartz vein for silica flux. And that's at 50 grams per ton. The production is the amount that they need of quartz. And so they produce 200,000 ounces a year. So this is just underground silica flux quarry. When you're lucky, you're real lucky. How about coffee? Okay. Maybe about 15 minutos.